Welcome to our deep dive into the cosmic microwave background, or CMB. The CMB is a faint glow of radiation that fills the universe, and it provides a snapshot of the early universe, shortly after the Big Bang. Discovered accidentally by Arno Penzias and Robert Wilson in 1965, this discovery earned them the Nobel Prize in Physics. The importance of the CMB in cosmology cannot be overstated, as it offers a wealth of information about the origins and evolution of the universe. In this video, we will explore the nature of the CMB, its discovery, and its significance in our understanding of the cosmos. The CMB is essentially the afterglow of the Big Bang, the event that created our universe around 13.8 billion years ago. This background radiation is a critical piece of evidence supporting the Big Bang theory, providing a direct link to the conditions of the early universe. Without the CMB, our understanding of the universe's beginnings would be much less clear. We'll delve into how the CMB fits into the Big Bang theory, the evidence it provides, and some of the alternative theories that have been proposed. One of the fascinating aspects of the CMB is its temperature, which is a remarkably uniform 2.725 Kelvin. This uniformity, or anisotropy, is a key feature of the CMB, indicating that the early universe was incredibly homogeneous. However, there are tiny fluctuations, known as anisotropies, which are critically important. These small temperature variations correspond to the seeds of all current structures in the universe, such as galaxies and clusters of galaxies. The discovery of the CMB by Penzias and Wilson was a landmark moment in the field of cosmology. Using a large horn antenna at Bell Labs, they stumbled upon this faint background noise that turned out to be the CMB. Following this groundbreaking discovery, a series of missions and experiments were conducted to study the CMB in more detail. Notably, the COBE satellite launched in 1989 provided the first precise measurements of the CMB, confirming its blackbody spectrum and detecting tiny temperature fluctuations. Building on COBE's success, the WMAP satellite, launched in 2001, produced a high-resolution map of the CMB, significantly enhancing our understanding of the early universe. Following WMAP, the Planck satellite, launched in 2009, provided even more detailed measurements, offering the most precise map of the CMB to date. These missions have been instrumental in refining our models of the universe's origins and evolution. Understanding the physics behind the CMB involves several key concepts. One crucial process is photon decoupling, which occurred when the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms, allowing photons to travel freely. This period, known as the recombination era, marked the universe becoming transparent to radiation. The CMB also exhibits a near-perfect blackbody spectrum, a hallmark of its origin from a hot, dense state. The CMB also provides evidence for various cosmological phenomena, such as the Doppler effect and redshift, which are essential in understanding the universe's expansion. Another significant effect observed in the CMB is the Sachs-Wolfe effect, which describes how gravitational potential wells affect the temperature of CMB photons. These physical processes offer insights into the conditions and dynamics of the early universe. CMB anisotropies, or tiny fluctuations in temperature, reveal a great deal about the large-scale structure of the universe. These temperature fluctuations are incredibly small, only a few parts per million, but they are crucial for understanding the distribution of matter and energy in the universe. Additionally, the polarization of the CMB, particularly B-mode polarization, provides evidence for the presence of primordial gravitational waves, offering a glimpse into the universe's inflationary period. Mapping the CMB involves creating detailed sky maps that show these tiny temperature variations. The techniques used in mapping include sophisticated instruments aboard satellites and ground-based telescopes. Data analysis methods, such as Fourier analysis and power spectra, help interpret these maps, revealing patterns that inform our understanding of the universe's geometry, composition, and evolution. These maps have led to key findings, including precise measurements of cosmological parameters. The CMB also plays a crucial role in determining the age of the universe. By analyzing the data from CMB observations, scientists can estimate the universe's age with remarkable precision. These estimates are consistent with other methods, such as studying globular clusters and radioactive decay. However, there are still uncertainties and challenges in these calculations. Accurate age determination is vital for piecing together the history and evolution of the cosmos, and the CMB provides a critical tool in this endeavor. The Big Bang Theory is our best explanation for the origin of the universe. It describes a moment around 13.8 billion years ago when the universe began expanding from an extremely hot and dense state. This theory explains the distribution of galaxies and the existence of the CMB. The initial state of the universe was a singularity, a point where density and temperature were infinitely high. From this singularity, the universe began to expand rapidly in an event known as cosmic inflation. During inflation, the universe expanded exponentially in a fraction of a second. As the universe expanded, it cooled, allowing particles to form. Quarks combined to form protons and neutrons, which later formed atomic nuclei. This period is known as nucleosynthesis and led to the formation of the first light elements, primarily hydrogen and helium. The CMB is a remnant of this early hot, dense state. It provides direct evidence of the Big Bang, capturing the conditions of the universe approximately 380,000 years after the event. By studying the CMB, we can learn about the universe's infancy. One of the key pieces of evidence supporting the Big Bang is the redshift of distant galaxies. Edwin Hubble discovered that galaxies are moving away from us, with their light shifted towards the red end of the spectrum. This observation suggests that the universe is expanding, consistent with the Big Bang theory. Another crucial piece of evidence is the abundance of light elements. The proportions of hydrogen, helium, and lithium observed in the universe align with predictions from Big Bang nucleosynthesis. This agreement supports the theory that these elements were formed in the first few minutes of the universe. The CMB also supports the Big Bang by showing us a nearly uniform universe with slight fluctuations. These fluctuations correspond to tiny density variations in the early universe, which later grew into galaxies and clusters. The detailed study of these anisotropies helps us understand the initial conditions of the universe. Alternative theories to the Big Bang have been proposed, but none match the predictive power of the Big Bang theory. The steady-state theory, for example, suggests that the universe has no beginning and is constantly creating new matter. However, it fails to explain the CMB and the observed distribution of galaxies. The historical development of the Big Bang theory involved many scientists. Georges Lemaitre first proposed the idea of an expanding universe in the 1920s. Later, George Gamow and his colleagues predicted the existence of the CMB, which was confirmed by Penzias and Wilson. The Big Bang theory has evolved over time with new discoveries. The concept of inflation, introduced by Alan Guth in the 1980s, addressed many problems of the original theory. Inflation explains the uniformity of the CMB and the large-scale structure of the universe. Observations of the CMB have refined our understanding of the Big Bang. Data from missions like COBE, WMAP, and Planck have provided detailed maps of the CMB, allowing precise measurements of cosmological parameters. These observations have confirmed many predictions of the Big Bang theory. The role of the CMB in the Big Bang theory is crucial. It serves as a snapshot of the early universe, revealing information about its temperature, composition, and structure. By studying the CMB, we can test predictions and refine our cosmological models. While the Big Bang theory is widely accepted, it continues to be tested and refined. New observations and experiments are constantly improving our understanding of the universe's origins. Future discoveries may provide further insights or even challenge our current theories. Understanding the Big Bang helps us answer fundamental questions about the universe. It informs us about the nature of space and time, the origins of matter and energy, and the processes that shape the cosmos. The study of the Big Bang and the CMB continues to be a vibrant and evolving field in cosmology. By exploring the Big Bang, we gain a deeper appreciation of the universe's complexity and beauty. The story of the universe's birth and evolution is a profound testament to the power of scientific inquiry. Through ongoing research, we continue to uncover the mysteries of our cosmic origins. The cosmic microwave background plays a vital role in validating the Big Bang theory. It serves as a direct snapshot of the universe when it was just 380,000 years old. This ancient light carries with it the imprint of the early universe's conditions. The uniformity of the CMB supports the idea of a hot, dense beginning. It shows that the early universe was remarkably homogeneous, with only tiny fluctuations. These fluctuations are the seeds of all current cosmic structures. CMB anisotropies are essential for understanding the universe's large-scale structure. The small temperature variations we observe today reflect the density differences in the early universe. These differences grew over billions of years into galaxies and clusters. The precise measurement of the CMB spectrum is a cornerstone of the Big Bang theory. The spectrum is a near-perfect blackbody, which is expected from the Big Bang model. This exact match between theory and observation is strong evidence for the Big Bang. The CMB also provides insight into the universe's rate of expansion. By analyzing the CMB, scientists can determine the Hubble constant, which describes the universe's expansion rate. This information is crucial for understanding the overall dynamics of the cosmos. Through the CMB, we can learn about the universe's age. The patterns observed in the CMB allow scientists to calculate the time elapsed since the Big Bang. These calculations have yielded an age of approximately 13.8 billion years. Another significant role of the CMB is in determining the universe's composition. The CMB data helps estimate the proportions of dark matter, dark energy, and ordinary matter. This understanding is vital for constructing accurate cosmological models. The polarization of the CMB offers additional insights into the early universe. Polarization patterns, especially the E mode and B mode, provide information about the reionization era and gravitational waves. These observations help refine our understanding of cosmic history. The CMB also tests and supports the theory of cosmic inflation. Inflation theory predicts specific patterns in the CMB anisotropies. Observations of these patterns have provided strong evidence that inflation occurred. By examining the Sachs-Wolfe effect in the CMB, we gain knowledge about the universe's gravitational potentials. This effect causes temperature fluctuations in the CMB due to gravitational redshifting. It helps us understand the distribution of large-scale structures. The CMB data has also helped resolve the horizon problem. The uniform temperature of the CMB across vast distances suggests that regions were once in contact. This observation supports the idea that inflation expanded the universe rapidly, connecting distant regions. CMB observations contribute to resolving the flatness problem. The geometry of the universe can be inferred from the CMB, and data indicates a flat universe. This observation aligns with predictions from inflationary models. By analyzing CMB anisotropies, scientists can probe the early universe's density fluctuations. These fluctuations give rise to the cosmic web of galaxies and clusters we see today. Understanding these initial conditions is crucial for cosmology. The CMB's role extends to testing alternative cosmological models. Any deviations from the expected CMB patterns could suggest new physics. Thus far, the CMB has strongly supported the Big Bang theory over alternatives. The wealth of information provided by the CMB continues to shape our understanding of the universe. As new data is collected, it further refines the Big Bang model and enhances our knowledge. The CMB remains a cornerstone of modern cosmology, offering a window into the universe's earliest moments. One of the most compelling pieces of evidence for the Big Bang is the redshift of galaxies. Edwin Hubble observed that galaxies are moving away from us, with their light shifted toward the red end of the spectrum. This redshift indicates that the universe is expanding. The abundance of light elements, such as hydrogen and helium, also supports the Big Bang theory. These elements were formed during the first few minutes of the universe in a process known as nucleosynthesis. The observed proportions of these elements match the predictions from the Big Bang model. The discovery of the cosmic microwave background provided a major breakthrough. The CMB is the afterglow of the Big Bang, offering a snapshot of the early universe. Its uniformity and spectrum are consistent with predictions from the Big Bang theory. The Hubble law further supports the idea of an expanding universe. It states that the velocity at which a galaxy moves away is proportional to its distance from us. This relationship is precisely what we would expect if the universe began with a Big Bang. Observations of the large-scale structure of the universe align with the Big Bang theory. The distribution of galaxies and galaxy clusters shows patterns that originated from early density fluctuations. These patterns are consistent with what we see in the CMB. The existence of cosmic inflation provides additional support. Inflation theory predicts certain characteristics in the CMB, such as uniformity and specific anisotropies. Observations have confirmed these predictions, strengthening the Big Bang model. The isotropy of the CMB is another crucial piece of evidence. The fact that the CMB temperature is nearly the same in every direction suggests a common origin. This uniformity aligns with the conditions expected shortly after the Big Bang. Gravitational waves detected by LIGO also offer support. These ripples in space-time were predicted by the Big Bang theory and detected as evidence of cosmic inflation. The presence of these waves confirms aspects of the early universe's rapid expansion. The distribution of galaxies across the universe follows a pattern that the Big Bang theory explains. These structures form from initial small density fluctuations, which grew over time. The way these fluctuations evolved matches the predictions from the Big Bang. The expansion rate of the universe, known as the Hubble constant, provides insight into the Big Bang. Precise measurements of this rate, especially from CMB data, match the model's predictions. This consistency supports the theory of a rapidly expanding universe. The observation of distant supernovae has also reinforced the Big Bang model. These exploding stars help measure the universe's expansion rate over time. Findings show that the universe's expansion is accelerating, a phenomenon explained by the Big Bang theory. The presence of dark matter and dark energy fits within the Big Bang framework. Observations of galaxy rotation curves and large-scale structures suggest these components. The Big Bang theory accommodates these findings, enhancing its explanatory power. The Sachs-Wolfe effect observed in the CMB is another piece of evidence. It describes how variations in gravitational potential affect CMB photons. This effect aligns with predictions from the Big Bang theory and inflation. Baryon acoustic oscillations provide a standard ruler for measuring cosmic distances. These oscillations are relics from the early universe's density fluctuations. Their current distribution helps map the expansion history, supporting the Big Bang. Finally, the age of the oldest star clusters aligns with the Big Bang timeline. Calculations of star ages are consistent with an approximately 13.8 billion-year-old universe. This consistency further corroborates the Big Bang model, tying together multiple lines of evidence. While the Big Bang theory is the leading explanation for the origin of the universe, several alternative theories have been proposed. One such theory is the steady-state theory. It suggests that the universe has no beginning or end and maintains a constant average density as it expands by continuously creating new matter. Another alternative is the ekpyrotic model, which proposes that the universe is the result of a collision between two three-dimensional worlds on a hidden fourth dimension. This theory seeks to explain some of the same phenomena as the Big Bang, such as the uniformity of the CMB, but without the concept of a singularity. The plasma cosmology theory posits that the dynamics of ionized gases, or plasma, play a significant role in the formation and evolution of the universe. This theory emphasizes electromagnetic forces over gravity and challenges some aspects of the Big Bang model, especially in explaining the large-scale structure of the cosmos. In the cyclic universe theory, the universe undergoes endless cycles of expansion and contraction. Each cycle begins with a Big Bang-like event and ends with a big crunch, where the universe collapses back into a dense state. This theory suggests that our current universe is just one phase in an infinite series of expansions and contractions. The quantum gravity theory seeks to unify general relativity with quantum mechanics, potentially offering new insights into the universe's origins. Some variants of this theory suggest that the universe could have originated from a quantum fluctuation in a vacuum, avoiding the need for a classical Big Bang singularity. Modified Newtonian dynamics, or MOND, is another alternative that modifies the laws of gravity to explain the observed dynamics of galaxies without invoking dark matter. While it doesn't directly address the universe's origin, it proposes different fundamental physics that could impact our understanding of cosmological evolution. String theory, a candidate for a theory of everything, suggests that the universe is composed of one-dimensional strings rather than point particles. Some versions of string theory include the concept of a multiverse, where our universe is just one of many. This could imply that the Big Bang was just a local event in a much larger and more complex multiverse. The holographic principle posits that all the information contained within a volume of space can be represented as a theory on the boundary of that space. This radical idea suggests that our three-dimensional universe might be a projection from a two-dimensional boundary, offering a different perspective on cosmological phenomena. The variable speed of light theory proposes that the speed of light was much higher in the early universe. This idea aims to address issues like the horizon problem and the flatness problem without invoking inflation. By altering a fundamental constant, this theory presents a dramatically different view of the universe's early conditions. The anthropic principle is more of a philosophical framework than a scientific theory. It suggests that the universe's laws appear fine-tuned for life because we exist to observe them. This principle is often invoked to explain why the constants of nature have the specific values that allow for the development of life and the universe as we know it. Loop quantum gravity, another attempt to merge general relativity and quantum mechanics, introduces the concept of quantum space-time. It suggests that space and time are quantized, and the Big Bang might be replaced by a big bounce, where a previous universe collapsed and then expanded into our current one. Some cosmologists have proposed the idea of a pre-Big Bang scenario. This theory suggests that the universe existed in some form before the Big Bang, and the event itself was a transition between two phases of the universe. This concept attempts to circumvent the singularity problem by suggesting a different initial state. The conformal cyclic cosmology theory, proposed by Roger Penrose, suggests that the universe goes through infinite cycles, each beginning with a Big Bang and ending in an eventual decay into pure energy. In this model, the end of one universe becomes the beginning of the next, in an endless sequence of aeons. The superfluid vacuum theory posits that space itself is a superfluid, and various cosmic phenomena can be explained by the dynamics of this superfluid. This theory challenges the traditional view of space as a mere backdrop, and suggests that vacuum properties can influence the universe's evolution. Finally, the idea of a fractal universe suggests that the structure of the universe exhibits self-similarity on various scales. This concept implies that the universe's large-scale structure might follow a fractal pattern, differing from the homogeneity and anisotropy assumed in the Big Bang model. The historical context of the Big Bang theory stretches back to the early 20th century. Before the Big Bang theory, the prevailing belief was that the universe was static and eternal. This idea was largely influenced by Newtonian physics and was widely accepted by scientists. In the 1910s, Albert Einstein's general theory of relativity revolutionized our understanding of gravity and the cosmos. Einstein's equations suggested that the universe should be either expanding or contracting. However, Einstein himself added a cosmological constant to maintain the idea of a static universe. Around the same time, astronomers like Vesto Melvin Slipher began observing redshifts in the light from distant galaxies. These redshifts indicated that galaxies were moving away from us, hinting at an expanding universe. This was a crucial piece of evidence that contradicted the static universe model. Georges Lemaitre, a Belgian priest and physicist, was one of the first to propose the idea of an expanding universe. In 1927, he suggested that the universe began from a primeval atom, or cosmic egg, that exploded, leading to expansion. Lemaitre's ideas laid the groundwork for what would become the Big Bang theory. In 1929, Edwin Hubble's observations provided strong evidence for an expanding universe. Hubble discovered that the velocity of a galaxy moving away from us is proportional to its distance. This relationship, now known as Hubble's law, was a key validation of the expanding universe model. During the 1940s, George Gamow and his colleagues developed the theoretical framework for the Big Bang. They predicted that if the universe had a hot and dense beginning, it should have left behind a relic radiation. This prediction set the stage for the discovery of the cosmic microwave background. The term Big Bang was coined in 1949 by astronomer Fred Hoyle. Ironically, Hoyle was a proponent of the steady-state theory and used the term derisively. Despite his intent, the name stuck and became the popular term for the theory of an expanding universe from a hot, dense state. In the 1960s, the discovery of the CMB by Arno Penzias and Robert Wilson provided the first direct evidence of the Big Bang. This discovery was a turning point, as it matched the predictions made by Gamow and his colleagues. The CMB's uniformity and blackbody spectrum were crucial confirmations. The 1980s saw the introduction of the theory of cosmic inflation by Alan Guth. Inflation proposed a rapid expansion of the universe in its first fractions of a second. This idea addressed several unresolved issues in the Big Bang theory, such as the horizon and flatness problems. Subsequent satellite missions like COBE, WMAP, and Planck have provided detailed measurements of the CMB. These missions have refined our understanding of the universe's early conditions and have helped confirm the predictions of inflation. They have also allowed for precise determination of cosmological parameters. The historical development of the Big Bang theory has involved contributions from many scientists. Figures like Lemaitre, Hubble, Gamow, and Guth played crucial roles in shaping the theory. Their collective work transformed our understanding of the universe's origin and evolution. The acceptance of the Big Bang theory was not immediate and faced significant resistance. Proponents of alternative theories, like the steady-state theory, challenged the Big Bang model for decades. However, accumulating evidence, particularly the CMB, gradually shifted scientific consensus. The Big Bang theory has continually evolved with new discoveries. Each generation of observations and experiments has refined our understanding and introduced new questions. This dynamic nature of the theory underscores the progress and adaptability of scientific inquiry. The historical context of the Big Bang is also marked by technological advancements. Innovations in telescopes, satellites, and detectors have enabled increasingly precise measurements. These tools have been essential in testing and validating the theoretical predictions of the Big Bang. Understanding the historical context of the Big Bang theory helps us appreciate the scientific journey. It highlights the collaborative and iterative nature of science, where new ideas build upon previous discoveries. This history continues to inspire future research and exploration in cosmology. The temperature of the cosmic microwave background is a critical aspect of our understanding of the universe. It is measured to be approximately 2.725 Kelvin, just above absolute zero. This uniform temperature is a key feature of the CMB. This near-uniform temperature indicates that the early universe was incredibly homogeneous. However, slight variations or anisotropies exist, which are crucial for understanding the formation of structures in the universe. These tiny temperature fluctuations are about 1 part in 100,000. The measurement of the CMB temperature was first made by the COBE satellite in 1989. COBE's observations confirmed that the CMB has a perfect blackbody spectrum. This means it matches the theoretical prediction of radiation from an early, hot, dense state. These temperature measurements are incredibly precise. Modern instruments like the Planck satellite have refined these measurements even further. Planck's data has provided a detailed map of temperature variations across the sky. The uniform temperature of the CMB supports the theory of cosmic inflation. Inflation predicts that the universe expanded rapidly, smoothing out any initial irregularities. This rapid expansion accounts for the observed uniformity. The slight anisotropies in the CMB temperature are significant. They represent the seeds of all current cosmic structures, such as galaxies and galaxy clusters. These tiny fluctuations grew over billions of years due to gravitational attraction. The temperature of the CMB also provides information about the universe's age. By studying the CMB, scientists can estimate the time elapsed since the Big Bang. This analysis has led to the current estimate of 13.8 billion years. The CMB temperature helps us understand the universe's composition. It provides insights into the amounts of dark matter, dark energy, and ordinary matter. These components influence the temperature fluctuations observed in the CMB. The cooling of the CMB over time is a result of the universe's expansion. As the universe expanded, the radiation stretched and cooled. This cooling process has led to the current temperature we observe today. The blackbody spectrum of the CMB is evidence for the Big Bang theory. A blackbody spectrum indicates it originated from a hot, dense state. This matches the predictions made by the Big Bang model. The temperature fluctuations in the CMB are measured in terms of their angular scale. These measurements reveal the size of structures in the early universe. By analyzing these scales, scientists can learn about the universe's initial conditions. The Sachs-Wolfe effect also impacts the CMB temperature. This effect describes how gravitational potentials affect the temperature of CMB photons. It provides additional information about the distribution of matter in the universe. The CMB temperature data helps test various cosmological models. By comparing observations with theoretical predictions, scientists can refine their models. This process has led to a deeper understanding of the universe's evolution. The precise measurement of the CMB temperature requires advanced technology. Instruments aboard satellites like COBE, WMAP, and Planck have made these measurements possible. These technologies continue to improve, offering even greater precision. Studying the CMB temperature is essential for cosmology. It provides a wealth of information about the universe's past, present, and future. By continuing to analyze the CMB, scientists hope to uncover more secrets about the cosmos. The cosmic microwave background is remarkably uniform across the sky. This uniformity, or anisotropy, suggests that the early universe was incredibly homogeneous. It supports the idea that the universe began from a hot, dense state and expanded uniformly. Despite this overall uniformity, tiny fluctuations in temperature exist. These fluctuations are called anisotropies and are crucial for understanding the universe's structure. They provide clues about the density variations in the early universe. The anisotropy of the CMB is a key prediction of the Big Bang theory. If the universe started from a singular event, we would expect it to be roughly the same in every direction. Observations confirm this, with the CMB appearing almost identical no matter where we look. Cosmic inflation explains this anisotropy. Inflation theory proposes that the universe underwent rapid expansion shortly after the Big Bang. This expansion smoothed out any initial irregularities, leading to the uniformity we observe today. Anisotropies, though small, play a significant role in cosmology. These tiny temperature differences correspond to regions of varying density. Over time, these regions grew into the galaxies and clusters we see today. The scale of these anisotropies provides information about the universe's geometry. By analyzing the size and distribution of these fluctuations, scientists can infer whether the universe is flat, open, or closed. Current data suggests that the universe is flat. The anisotropy of the CMB also implies that different regions of the universe were once in causal contact. This means they were close enough to influence each other before inflation pushed them apart. This observation supports the theory of cosmic inflation. Measurements of the CMB anisotropies are incredibly precise. Satellites like COBE, WMAP, and Planck have provided detailed maps of these fluctuations. These maps are essential for testing and refining cosmological models. The uniformity of the CMB challenges alternative theories. Models that do not predict a homogeneous early universe struggle to explain the observed anisotropy. This uniformity is one of the strongest pieces of evidence for the Big Bang and inflation. Tiny variations in the CMB temperature are measured in microkelvins. These small differences reveal the initial conditions of the universe. Understanding these conditions helps scientists reconstruct the history of cosmic evolution. The anisotropy of the CMB also has implications for the large-scale structure of the universe. It suggests that the universe is the same everywhere on large scales, known as the cosmological principle. This principle is a foundation of modern cosmology. The detailed study of CMB anisotropies has led to significant discoveries. These include insights into the universe's composition, age, and rate of expansion. The data from CMB observations continues to be a goldmine for cosmologists. The uniformity and anisotropy of the CMB provide a benchmark for testing new theories. Any viable cosmological model must account for these observed features. This requirement ensures that new theories are consistent with existing data. The anisotropy of the CMB also helps in understanding the universe's initial conditions. It indicates a smooth beginning with only tiny perturbations. These initial conditions set the stage for the complex structures we observe today. Studying the uniformity and anisotropy of the CMB deepens our understanding of the cosmos. It connects the large-scale structure of the universe to its earliest moments. This connection is crucial for unraveling the history and fate of the universe. Anisotropies in the cosmic microwave background are tiny temperature fluctuations that break its uniformity. These slight variations are incredibly significant for understanding the universe's structure. They represent the initial seeds of galaxies and large-scale structures. The anisotropies are measured in microkelvins, revealing minute differences in temperature across the sky. These small fluctuations correspond to regions of different densities in the early universe. Over billions of years, these regions evolved into the complex cosmic web we observe today. Detailed maps of these anisotropies have been created by missions such as COBE, WMAP, and Planck. These maps show the intricate patterns of temperature variations. Analyzing these patterns helps scientists understand the initial conditions of the universe. One of the key features of these anisotropies is their power spectrum. The power spectrum shows the intensity of fluctuations at different scales. Peaks in this spectrum correspond to specific physical processes in the early universe. The first peak in the power spectrum indicates the scale of sound waves in the early universe. These acoustic oscillations were caused by the interplay between gravity and pressure in the primordial plasma. This peak provides information about the universe's overall geometry. Higher peaks in the power spectrum give insights into the universe's composition. They help determine the relative amounts of dark matter, dark energy, and ordinary matter. This data is crucial for constructing accurate cosmological models. The anisotropies also provide evidence for the theory of cosmic inflation. Inflation predicts a specific pattern of fluctuations that match what we observe. The detailed agreement between inflationary predictions and CMB observations strengthens the case for this theory. Polarization of the CMB is another important aspect linked to anisotropies. When light from the early universe scattered off electrons, it became polarized. Studying this polarization helps us learn about the universe's reionization and the influence of gravitational waves. The Sachs-Wolfe effect is another phenomenon related to anisotropies. This effect describes how fluctuations in gravitational potential affect the temperature of the CMB. It provides additional information about the distribution of matter in the universe. By studying anisotropies, scientists can test different models of the universe's evolution. These tiny fluctuations act as a cosmic fingerprint, allowing us to compare theoretical predictions with observed data. This process helps refine our understanding of fundamental physics. The scale of anisotropies can also reveal information about the horizon problem. The uniformity of the CMB across vast distances suggests that distant regions were once in causal contact. This observation supports the idea of rapid expansion, as proposed by inflation. Anisotropies help us understand the concept of dark energy. The way these fluctuations grow over time provides clues about the mysterious force driving the universe's accelerated expansion. Dark energy's effects are imprinted in the large-scale structure we observe today. Studying the anisotropies also aids in determining the universe's age. The patterns in the CMB allow scientists to calculate how long it has been since the Big Bang. This method provides a precise estimate of the universe's age, consistent with other measurements. The analysis of anisotropies continues to evolve with new data and techniques. Advanced instruments and deeper observations refine our understanding of these tiny fluctuations. Each new piece of data helps build a more comprehensive picture of the cosmos. The significance of anisotropies extends to testing the limits of current theories. As we probe these small temperature variations, we push the boundaries of our knowledge. This exploration could lead to new discoveries about the fundamental nature of the universe. The spectrum of the cosmic microwave background is a crucial aspect of its study. It exhibits a near-perfect blackbody spectrum, which is a key prediction of the Big Bang theory. This blackbody spectrum indicates that the CMB originated from a hot, dense state. This spectrum peaks at microwave wavelengths, corresponding to a temperature of about 2.725 Kelvin. The precise shape of the CMB spectrum matches the theoretical predictions for radiation from the early universe. This agreement provides strong evidence for the Big Bang model. The blackbody nature of the CMB spectrum was confirmed by the COBE satellite. COBE's measurements showed that the CMB fits the blackbody curve almost perfectly. This was a significant milestone in validating the Big Bang theory. Planck satellite data has provided even more detailed measurements of the CMB spectrum. These observations have refined our understanding of the universe's early conditions. The spectrum's precision helps scientists test various cosmological models. The blackbody spectrum of the CMB results from the thermal equilibrium of photons in the early universe. During the recombination era, photons decoupled from matter and began to travel freely through space. This decoupling left behind the blackbody radiation we observe today. Small deviations from the perfect blackbody spectrum can provide additional insights. These deviations, or spectral distortions, can reveal processes that occurred in the early universe. Studying these distortions helps us understand the detailed physics of the primordial plasma. One type of spectral distortion is the Sunyaev-Zeldovich effect. This effect occurs when CMB photons interact with hot electrons in galaxy clusters. It causes a shift in the CMB spectrum, providing information about the cluster's properties. Another potential source of spectral distortions is energy release from decaying particles or primordial black holes. These processes could leave imprints on the CMB spectrum. Detecting such imprints would offer clues about the nature of dark matter and early universe phenomena. The spectrum also carries information about the universe's expansion rate. The redshift of the CMB photons stretches their wavelengths, cooling the radiation over time. This cooling process is reflected in the observed blackbody spectrum. The precise measurement of the CMB spectrum requires advanced technology. Instruments on satellites like COBE, WMAP, and Planck have been designed to achieve this. These instruments must account for various sources of noise and interference. The CMB spectrum helps us understand the universe's composition. The presence of dark matter, dark energy, and ordinary matter affects the spectrum's shape. By analyzing the spectrum, scientists can estimate the proportions of these components. The uniformity of the CMB spectrum across the sky supports the anisotropy of the early universe. It indicates that the conditions were the same in all directions when the CMB was emitted. This uniformity aligns with the predictions of the Big Bang and inflation theories. The study of the CMB spectrum continues to be an active area of research. New observations and technologies promise to provide even more detailed data. This ongoing research aims to uncover more about the universe's origins and evolution. Understanding the spectrum of the CMB is fundamental to cosmology. It provides a wealth of information about the early universe's conditions and subsequent evolution. Each new discovery from the CMB spectrum adds to our knowledge of the cosmos. The blackbody spectrum of the CMB remains one of the most compelling pieces of evidence for the Big Bang. It offers a direct link to the universe's infancy, allowing scientists to probe the fundamental nature of reality. The continued study of this spectrum promises to reveal even more about our cosmic origins. Measuring the cosmic microwave background requires highly sensitive instruments. These instruments must detect faint microwave radiation from space with great precision. The data collected provides insights into the universe's early conditions. Satellites like COBE, WMAP, and Planck have been instrumental in measuring the CMB. These satellites are equipped with sophisticated sensors designed to detect minute temperature variations. They orbit Earth, away from atmospheric interference, to get a clear view of the cosmos. COBE was the first satellite to measure the CMB spectrum accurately. It confirmed that the CMB has a near-perfect blackbody spectrum. COBE also detected tiny temperature fluctuations, paving the way for more detailed studies. WMAP improved upon COBE's measurements by providing higher resolution maps. It mapped the temperature fluctuations across the entire sky with unprecedented detail. This data helped refine estimates of the universe's age, composition, and rate of expansion. Planck took CMB measurements to the next level with even higher sensitivity and resolution. It provided the most detailed maps of the CMB to date. Planck's data has been crucial for testing cosmological models and understanding the early universe. Ground-based observatories also play a role in measuring the CMB. Telescopes like the Atacama Cosmology Telescope and the South Pole Telescope operate in remote locations. These locations are chosen for their clear, dry conditions, which minimize atmospheric interference. Balloon-borne experiments like Boomerang and Arcade complement satellite and ground-based observations. These experiments carry instruments high into the stratosphere. By flying above most of the atmosphere, they can measure the CMB with reduced interference. The instruments used to measure the CMB include radiometers and bolometers. Radiometers measure the power of the incoming microwave radiation. Bolometers detect radiation by measuring tiny changes in temperature caused by incoming photons. Interferometry is another technique used to measure the CMB. It involves combining signals from multiple telescopes to create a detailed image. This technique increases the resolution and sensitivity of the observations. Polarization-sensitive instruments are essential for studying the CMB's polarization. These instruments detect the orientation of the microwave radiation. Polarization data provides additional information about the early universe and cosmic inflation. Calibration is critical for accurate CMB measurements. Instruments must be precisely calibrated to ensure that the data is accurate. Calibration involves comparing the instrument's readings to known sources and making necessary adjustments. Data analysis techniques are equally important. The raw data collected by instruments is processed using complex algorithms. These algorithms remove noise and interference, allowing scientists to extract meaningful information. Advanced computing plays a vital role in processing CMB data. The vast amount of data collected requires powerful computers to analyze. Supercomputers help process this data, generating detailed maps and spectra of the CMB. International collaborations enhance CMB measurement techniques. Scientists from around the world work together on missions and experiments. This collaboration brings together expertise and resources, leading to more precise and comprehensive measurements. Future missions and technologies promise to further improve CMB measurements. Upcoming projects aim to provide even higher resolution maps and more detailed polarization data. These advancements will continue to deepen our understanding of the universe's origins. In 1965, Arno Penzias and Robert Wilson made a groundbreaking discovery while working at Bell Labs. They were using a large horn antenna to study radio signals bounced off satellites. Instead, they detected a persistent background noise that puzzled them. This noise was uniform in all directions and did not vary with time. Penzias and Wilson initially suspected technical issues or environmental interference. They meticulously checked their equipment and even cleared out nesting pigeons from the antenna. Despite their efforts, the noise persisted, leading them to consider a more profound source. Around the same time, Robert Dicke and his team at Princeton University were working on a theory about cosmic microwave radiation. They predicted this radiation would be a remnant of the Big Bang. When Penzias and Wilson learned about Dicke's work, they realized the significance of their finding. The noise they detected was, in fact, the cosmic microwave background radiation. This discovery provided the first direct evidence supporting the Big Bang theory. The detection of the CMB was a monumental moment in cosmology. It confirmed the theoretical predictions about the universe's early state. Penzias and Wilson's work earned them the Nobel Prize in Physics in 1978. Their discovery also highlighted the importance of serendipity in scientific research. It was a chance encounter with unexpected data that led to a major breakthrough. This underscores the value of curiosity and persistence in scientific endeavors. The horn antenna used by Penzias and Wilson became an iconic symbol of their discovery. Located in Holmdel, New Jersey, it was originally intended for satellite communication. Today, it stands as a testament to one of the most significant discoveries in cosmology. Their findings sparked a flurry of further research into the CMB. Scientists worldwide began to study this faint background radiation in greater detail. This research has vastly expanded our understanding of the universe's origins and evolution. The work of Penzias and Wilson paved the way for subsequent CMB experiments. Their discovery set the stage for missions like COBE, WMAP, and Planck. These missions have provided increasingly detailed maps of the CMB, refining our cosmological models. Their collaboration with the Princeton team exemplifies the collaborative nature of scientific discovery. Sharing information and insights was crucial in realizing the significance of the CMB. This spirit of cooperation continues to drive advancements in cosmology. Penzias and Wilson's discovery also had a profound impact on public understanding of the universe. It brought the Big Bang theory into mainstream consciousness. This shift has influenced how we perceive our place in the cosmos. Their work is a classic example of how observational astronomy can lead to theoretical breakthroughs. By carefully analyzing their data, they made a connection that fundamentally changed cosmology. This synergy between observation and theory is central to scientific progress. The discovery highlighted the role of technology in advancing our understanding of the universe. The horn antenna, though originally designed for another purpose, became a tool for cosmological discovery. Innovations in technology continue to drive new discoveries in astronomy. Penzias and Wilson's experience also shows the importance of being open to unexpected results. Their willingness to explore an anomalous signal led to a groundbreaking discovery. This openness is essential for making significant scientific advancements. Their discovery of the CMB remains one of the most significant achievements in the history of science. It provided crucial evidence for the Big Bang theory and opened new avenues for research. The legacy of their work continues to inspire scientists and researchers around the world. Following the discovery by Penzias and Wilson, early experiments and observations of the CMB became a priority in cosmology. Scientists aimed to confirm and expand upon their findings with more detailed measurements. These early efforts laid the groundwork for our current understanding of the CMB. One of the first significant follow-up experiments was conducted by David Wilkinson and Peter Roll at Princeton University. They used a ground-based telescope to measure the CMB and confirmed its isotropy. Their results reinforced the idea that the CMB was a remnant from the early universe. Throughout the 1970s, numerous balloon-borne experiments were launched to study the CMB. Balloons offered a way to get above much of the Earth's atmosphere, reducing interference. These experiments provided better data on the CMB's temperature and its small-scale fluctuations. The Mariner 2 spacecraft, while primarily a planetary mission, also contributed to CMB studies. In 1967, it measured the microwave background, providing an independent verification of its existence. This reinforced the conclusion that the CMB was a universal phenomenon. The Cosmic Background Explorer, or COBE, launched in 1989, marked a major milestone. COBE's instruments measured the CMB with unprecedented precision. It confirmed the blackbody spectrum of the CMB and detected small anisotropies, providing critical data for cosmologists. COBE carried three main instruments: the far-infrared absolute spectrophotometer, FIRAS, the differential microwave radiometer, DMR, and the diffuse infrared background experiment, DERBY. FIRAS confirmed the blackbody spectrum, while DMR mapped temperature fluctuations. These early experiments were crucial in establishing the standard model of cosmology. They provided the first detailed evidence supporting the Big Bang theory. By confirming the theoretical predictions, they helped solidify the CMB's role in our understanding of the universe. Ground-based observatories also contributed significantly. Telescopes like the Cosmic Anisotropy Telescope in Chile and the Owens Valley Radio Observatory in California provided detailed measurements of the CMB. These observations were vital for understanding the universe's large-scale structure. The 1990s saw the deployment of more sophisticated balloon experiments like Boomerang and Maxima. These experiments provided high-resolution maps of the CMB anisotropies. Their data helped refine estimates of cosmological parameters, such as the universe's age and composition. In addition to balloon and satellite missions, ground-based interferometers like the Degree Angular Scale Interferometer, DASI, provided crucial data. DASI was the first to detect polarization in the CMB, opening a new window into the early universe's conditions. The Tenerife experiment, conducted in the Canary Islands, was another important early project. It measured the CMB at multiple frequencies to separate it from galactic foregrounds. This helped improve the accuracy of CMB observations by reducing contamination from other sources. These early efforts were not without challenges. Technical limitations and atmospheric interference posed significant hurdles. However, the perseverance of scientists and engineers led to increasingly accurate and detailed measurements. The data from these early experiments was instrumental in shaping modern cosmological theories. They provided the first clear pictures of the early universe's structure. This, in turn, helped refine models of cosmic inflation and large-scale structure formation. Each of these early observations built upon the work of Penzias and Wilson. Together, they confirmed the CMB's existence, mapped its anisotropies, and measured its spectrum. This collaborative effort laid the foundation for the advanced missions and discoveries that followed. As technology advanced, these early experiments transitioned into more sophisticated missions. They set the stage for subsequent projects like WMAP and Planck, which have provided even more detailed views of the CMB. The legacy of these early efforts continues to inform and inspire current and future cosmological research. The COBE satellite mission, launched in 1989, marked a significant advancement in the study of the cosmic microwave background. COBE, short for the Cosmic Background Explorer, was designed to measure the diffuse infrared and microwave radiation from the early universe. Its findings had profound implications for cosmology. COBE carried three primary instruments: the differential microwave radiometer, the far-infrared absolute spectrophotometer, and the diffuse infrared background experiment. Each instrument played a crucial role in mapping and analyzing the CMB. Together, they provided a comprehensive view of the early universe. The differential microwave radiometer, or DMR, was tasked with measuring temperature fluctuations in the CMB. It detected tiny variations, or anisotropies, across the sky. These anisotropies corresponded to density variations in the early universe, which eventually led to the formation of galaxies and clusters. The far-infrared absolute spectrophotometer, known as FIRAS, measured the spectrum of the CMB. FIRAS confirmed that the CMB had a near-perfect blackbody spectrum. This was a critical confirmation of the Big Bang theory, as it matched the theoretical predictions for the early universe's radiation. The diffuse infrared background experiment, or DIRBY, searched for the cosmic infrared background. While its primary goal wasn't focused on the CMB, DIRBY's data complemented the findings of DMR and FIRAS. It helped map out the infrared emissions from various cosmic sources. One of COBE's most significant achievements was the confirmation of the CMB's blackbody spectrum. This finding provided strong evidence for the Big Bang model. The precise measurements showed that the early universe was indeed hot and dense, as predicted. COBE also detected the first detailed maps of the CMB anisotropies. These tiny temperature fluctuations were crucial for understanding the universe's large-scale structure. The patterns observed by COBE provided insights into the initial conditions of the cosmos. The mission's success was a major milestone for cosmology. COBE's data helped solidify the Big Bang theory as the leading explanation for the universe's origin. It also laid the groundwork for future CMB missions, which would build on its pioneering observations. COBE's results earned the team significant recognition. In 2006, John Mather and George Smoot, two of the principal investigators, were awarded the Nobel Prize in Physics. Their work with COBE was hailed as a monumental achievement in understanding the universe. The satellite's findings also had implications for the theory of cosmic inflation. The anisotropies detected by COBE were consistent with predictions from inflationary models. This provided indirect evidence supporting the idea that the universe underwent rapid expansion shortly after the Big Bang. COBE's success demonstrated the importance of satellite-based observations for cosmology. Ground-based telescopes and balloon experiments had limitations due to atmospheric interference. By operating in space, COBE avoided these issues and achieved unprecedented precision. The data collected by COBE has been extensively analyzed and reanalyzed over the years. Its legacy continues to influence contemporary cosmological research. The mission set a high standard for accuracy and precision in CMB measurements. COBE's instruments and technology paved the way for subsequent missions like WMAP and Planck. These missions benefited from the advancements and lessons learned from COBE. They aim to provide even more detailed maps and spectra of the CMB. The success of COBE highlighted the collaborative nature of modern science. Scientists, engineers, and researchers from various institutions worked together to achieve the mission's goals. This teamwork was essential for overcoming the technical challenges and ensuring the mission's success. COBE's legacy is a testament to the power of curiosity and innovation in science. Its discoveries have deepened our understanding of the universe and its origins. The mission's contributions continue to inspire new generations of scientists and researchers in the field of cosmology. The WMAP satellite mission, which stands for Wilkinson Microwave Anisotropy Probe, was launched in 2001. WMAP's primary goal was to map the temperature fluctuations in the cosmic microwave background with greater precision than ever before. It built on the successes of the COBE mission and provided detailed data that transformed our understanding of the universe. WMAP operated at multiple frequencies to differentiate between the CMB and foreground emissions. This multi-frequency approach allowed for the removal of galactic and extragalactic noise, resulting in clearer maps of the CMB. These maps revealed intricate details about the universe's early conditions. One of WMAP's significant achievements was the precise measurement of the age of the universe. By analyzing the CMB data, scientists determined that the universe is approximately 13.8 billion years old. This measurement has been widely accepted and corroborated by other methods. WMAP also provided valuable data on the universe's composition. It confirmed that ordinary matter makes up only a small fraction of the total mass-energy content of the universe. The majority is composed of dark matter and dark energy, with dark energy driving the accelerated expansion of the universe. The mission's findings on the geometry of the universe were groundbreaking. WMAP data indicated that the universe is flat, meaning it will continue to expand indefinitely. This discovery has significant implications for cosmological models and our understanding of the universe's fate. WMAP's detailed maps of the CMB anisotropies allowed scientists to study the large-scale structure of the universe. These maps showed how tiny fluctuations in the early universe grew into the vast cosmic structures we see today. The data provided insights into the process of structure formation. The polarization of the CMB was another key focus of WMAP. The satellite measured both E-mode and B-mode polarization, providing information about the universe's rionization era. This era, which occurred after the first stars formed, left an imprint on the CMB's polarization patterns. WMAP's data supported the theory of cosmic inflation. The patterns of anisotropies observed by WMAP were consistent with inflationary models. This provided strong evidence that the universe underwent a rapid expansion shortly after the Big Bang. The mission's results also contributed to refining the Hubble constant, the rate of the universe's expansion. WMAP's measurements of the CMB helped determine this constant with greater accuracy. This information is crucial for understanding the dynamics of the universe's expansion. WMAP operated for 9 years, far exceeding its initial mission plan. During this time, it continuously gathered data, providing an extensive and detailed dataset. This long duration allowed for the refinement of its measurements and the reduction of uncertainties. The success of WMAP highlighted the importance of precision and accuracy in cosmological observations. Its findings have become benchmarks in the field of cosmology. The data from WMAP continues to be used in research and has set a high standard for future missions. WMAP's legacy includes its role in confirming the lambda cold dark matter model, or lambda CDM model. This model describes the universe as consisting of dark energy, dark matter, and ordinary matter. It has become the standard model of cosmology, largely due to WMAP's contributions. The collaboration between NASA and various research institutions was crucial for WMAP's success. The mission brought together scientists, engineers, and researchers from around the world. This collaborative effort was essential for achieving the mission's ambitious goals. WMAP's findings have had a profound impact on our understanding of the universe. The detailed maps and precise measurements provided by the mission have answered many fundamental questions in cosmology. However, they have also opened up new avenues for research and exploration. The Wilkinson microwave anisotropy probe set the stage for subsequent missions like Planck. By pushing the boundaries of what we could observe, WMAP expanded our knowledge of the cosmos. Its contributions to cosmology continue to resonate, inspiring future generations of scientists and researchers. The Planck satellite mission, launched in 2009, aimed to further refine our understanding of the cosmic microwave background. It was designed to provide even more detailed measurements than WMAP, with higher sensitivity and resolution. Planck's observations have significantly advanced our knowledge of the universe. Planck carried 2 instruments, the low-frequency instrument and the high-frequency instrument. These instruments covered a wide range of frequencies, allowing for detailed studies of the CMB's temperature and polarization. The combination of these instruments provided unprecedented accuracy. One of Planck's primary achievements was producing the most detailed maps of the CMB ever created. These maps revealed intricate patterns of temperature fluctuations and polarization. The data allowed scientists to study the universe's early conditions with exceptional precision. Planck's measurements confirmed and refined the findings of previous missions like COBE and WMAP. It provided a more precise estimate of the universe's age, confirming it to be about 13.8 billion years old. This consistency across different missions strengthens the reliability of these measurements. The data from Planck has provided critical insights into the universe's composition. It confirmed the presence of dark matter and dark energy, refining their proportions. According to Planck's findings, dark energy makes up about 68% of the universe, dark matter about 27%, and ordinary matter about 5%. Planck also contributed to our understanding of the universe's geometry. Its high-precision measurements confirmed that the universe is flat with remarkable accuracy. This finding has significant implications for the future expansion of the universe. The mission provided detailed information about the ionization era. Planck's observations of CMB polarization offered insights into this period when the first stars and galaxies formed. This data helps us understand how the universe evolved from the cosmic dark ages to its current state. Planck's findings supported the theory of cosmic inflation. The detailed patterns of anisotropies and polarization observed by Planck matched the predictions of inflationary models. This provides strong evidence that the universe underwent rapid expansion shortly after the Big Bang. One of the mission's notable achievements was the measurement of the CMB's temperature fluctuations on small scales. These high-resolution measurements revealed fine details of the early universe's structure. This information is crucial for understanding the formation and evolution of galaxies and large-scale structures. Planck's data also improved our understanding of the Hubble constant. Its precise measurements of the CMB contributed to a more accurate determination of the universe's expansion rate. This helps resolve discrepancies between different methods of measuring the Hubble constant. The mission's success highlighted the importance of international collaboration. The Planck satellite was a joint project of the European Space Agency and various scientific institutions worldwide. This collaboration brought together expertise and resources from around the globe. Planck's findings have had a profound impact on cosmology. The mission's detailed data has refined our models of the universe and answered many fundamental questions. However, it has also raised new questions, driving further research and exploration. The legacy of the Planck mission continues to influence contemporary cosmology. Its data is still being analyzed, providing ongoing insights into the universe's early conditions. Future missions will build on Planck's findings, further advancing our understanding of the cosmos. Planck's contributions extend beyond cosmology. Its precise measurements have applications in other fields of astrophysics and fundamental physics. The techniques and technologies developed for Planck are being used in various scientific endeavors. The Planck satellite mission has set a new standard for precision in cosmological observations. Its detailed maps and accurate measurements have significantly advanced our understanding of the universe. The mission's success continues to inspire future generations of scientists and researchers. Photon decoupling is a pivotal event in the history of the universe. It occurred about 380,000 years after the Big Bang, marking the moment when photons could travel freely through space. This period is also known as the era of recombination. Before decoupling, the universe was a hot, dense plasma of photons, electrons, and protons. Photons constantly scattered off electrons, making the universe opaque. This scattering prevented photons from traveling long distances. As the universe expanded, it cooled down. When the temperature dropped to about 3000 Kelvin, protons and electrons combined to form neutral hydrogen atoms. This process is called recombination, as it resulted in the formation of stable atoms for the first time. With the formation of neutral atoms, photons no longer scattered off free electrons. This allowed photons to travel unimpeded, leading to the universe becoming transparent. This moment of photon decoupling left an imprint that we now observe as the cosmic microwave background. The photons that decoupled during this era have been traveling through space ever since. They carry information about the conditions of the early universe. By studying the CMB, scientists can learn about the temperature, density, and composition of the universe at that time. Photon decoupling also marks the end of the plasma state of the universe. The transition from a plasma to a neutral gas had significant implications for the formation of cosmic structures. It set the stage for the growth of galaxies and other large-scale structures. The CMB provides a snapshot of the universe at the moment of photon decoupling. The temperature fluctuations observed in the CMB correspond to density variations in the early universe. These variations eventually led to the formation of stars, galaxies, and clusters. The process of photon decoupling is crucial for understanding the universe's evolution. It provides insights into the physical conditions of the early universe. This understanding helps scientists build accurate models of cosmic history. Photon decoupling also has implications for the study of dark matter and dark energy. The behavior of photons during this period can provide clues about the nature and distribution of these mysterious components. This information is essential for constructing comprehensive cosmological models. The study of photon decoupling involves precise measurements of the CMB. Instruments on satellites like COBE, WMAP, and Planck have provided detailed data on the CMB's temperature and polarization. This data helps refine our understanding of the decoupling process. Photon decoupling is a key topic in the study of cosmic inflation. The conditions at the time of decoupling reflect the effects of inflation on the early universe. By analyzing the CMB, scientists can test predictions of inflationary models. The concept of photon decoupling is also important for understanding the universe's large-scale structure. The initial density fluctuations observed in the CMB grew into the vast cosmic web we see today. This growth was influenced by the physics of the decoupling era. Photon decoupling provides a direct link between the Big Bang and the present-day universe. The CMB acts as a cosmic relic, preserving information from a critical period in the universe's history. Studying this relic helps bridge our understanding across vast spans of time. Advances in technology continue to improve our understanding of photon decoupling. New instruments and techniques allow for more precise measurements of the CMB. These advancements will further enhance our knowledge of this fundamental event in cosmic history. The significance of photon decoupling extends beyond cosmology. It provides insights into fundamental physics, including the behavior of particles and radiation. The study of photon decoupling continues to be a vital area of research in understanding the universe's origins and evolution. The recombination era is a critical phase in the universe's history, occurring around 380,000 years after the Big Bang. During this period, the temperature of the universe dropped sufficiently for protons and electrons to combine and form neutral hydrogen atoms. This recombination of particles had profound implications for the evolution of the cosmos. Before recombination, the universe was an opaque plasma of protons, electrons, and photons. Photons constantly scattered off free electrons, preventing them from traveling long distances. This scattering made the universe opaque and impenetrable to light. As the universe expanded, it cooled down. When the temperature fell to about 3000 Kelvin, protons and electrons could combine to form neutral hydrogen atoms. This process, known as recombination, reduced the number of free electrons available to scatter photons. With fewer free electrons, photons could travel freely through space. This transition marked the end of the universe's opaque plasma state and the beginning of a transparent universe. The release of these photons is observed today as the cosmic microwave background. The recombination era left a lasting imprint on the CMB. The temperature and density variations from this time are preserved in the CMB's fluctuations. These fluctuations provide a snapshot of the universe's conditions during recombination. Recombination also set the stage for the formation of the first cosmic structures. The density fluctuations present in the CMB served as the seeds for galaxies and clusters. Over time, gravitational forces amplified these fluctuations, leading to the large-scale structures we see today. The process of recombination is essential for understanding the universe's thermal history. It marked a significant cooling phase that allowed the universe to transition from a hot, dense plasma to a cooler, neutral gas. This transition was crucial for the development of the cosmic web. Recombination also has implications for the study of dark matter. The way matter clumped together during this era can provide clues about the properties and distribution of dark matter. Analyzing the CMB helps scientists infer the influence of dark matter on early structure formation. The era of recombination is closely linked to the concept of photon decoupling. As neutral atoms formed, photons decoupled from matter and began to travel freely. This decoupling left behind the CMB, which we observe as a relic of this transformative period. Understanding recombination helps refine cosmological models. Accurate models of this era are essential for predicting the observed properties of the CMB. These models must account for the detailed physics of how particles combined and photons decoupled. The study of recombination involves precise measurements and advanced simulations. Data from satellites like COBE, WMAP, and Planck provide detailed observations of the CMB. These observations help test and validate theoretical models of the recombination era. Recombination is also relevant for understanding the ionization history of the universe. The transition to a neutral state was followed by reionization when the first stars and galaxies formed. Studying recombination provides context for these later phases of cosmic evolution. The cooling of the universe during recombination had lasting effects on its overall structure. It allowed the first neutral atoms to form, setting the stage for chemical complexity. This complexity eventually led to the formation of stars, planets, and life. Advances in technology continue to enhance our understanding of recombination. Improved instruments and computational techniques allow for more detailed studies. These advancements will help uncover new aspects of this critical phase in cosmic history. Recombination remains a vibrant area of research in cosmology. It connects the early universe's conditions to the formation of large-scale structures. Ongoing studies of recombination deepen our understanding of the universe's origins and its subsequent evolution. Blackbody radiation is a fundamental concept in understanding the cosmic microwave background. It refers to the radiation emitted by an idealized object that absorbs all incident electromagnetic radiation, regardless of frequency or angle. This radiation is solely dependent on the object's temperature. The cosmic microwave background exhibits a near-perfect blackbody spectrum. This means the CMB's radiation matches what we would expect from an ideal blackbody at a temperature of about 2.725 Kelvin. This is one of the strongest pieces of evidence supporting the Big Bang theory. A blackbody spectrum has a distinctive shape, characterized by a peak at a specific wavelength. For the CMB, this peak occurs in the microwave range. The precise measurement of this spectrum by the COBE satellite was a major milestone in cosmology. The Planck law describes the intensity of blackbody radiation at different wavelengths. It shows how the radiation depends on the temperature of the emitting body. The CMB's spectrum fits this law perfectly, indicating it originated from a hot, dense early universe. The concept of blackbody radiation was first introduced by Max Planck in the early 20th century. Planck's work on blackbody radiation led to the development of quantum theory. This theoretical foundation is crucial for understanding the thermal history of the universe. Blackbody radiation is isotropic, meaning it is the same in all directions. This anisotropy is observed in the CMB, supporting the idea that the early universe was homogeneous and isotropic. Tiny anisotropies in the CMB provide information about the initial density fluctuations. The perfect blackbody spectrum of the CMB suggests that the early universe was in thermal equilibrium. During this time, photons, electrons, and protons were constantly interacting, maintaining a uniform temperature. This equilibrium state ended with the era of recombination. The spectrum's shape is not affected by the expansion of the universe. As the universe expanded, the CMB's wavelength stretched, but its blackbody nature remained unchanged. This stretching caused the CMB to cool to its current temperature of 2.725 Kelvin. Studying blackbody radiation in the CMB helps us understand the universe's composition. The spectrum provides clues about the amounts of ordinary matter, and dark energy. These components influence the overall shape and features of the CMB spectrum. The Sunyaev-Zeldovich effect is an important phenomenon related to blackbody radiation. It occurs when CMB photons interact with hot electrons in galaxy clusters, distorting the blackbody spectrum. This effect provides valuable information about the properties of these clusters. Deviations from the perfect blackbody spectrum can reveal new physics. Any unexpected spectral distortions could indicate processes not accounted for in current models. Studying these deviations helps refine our understanding of the early universe. The blackbody nature of the CMB also plays a role in testing alternative cosmological theories. Any theory of the universe's origin and evolution must explain the CMB's perfect blackbody spectrum. This requirement acts as a benchmark for evaluating different models. Instruments designed to measure the CMB are calibrated against blackbody sources. These sources provide a reference for ensuring the accuracy of the measurements. Precise calibration is essential for detecting the tiny temperature fluctuations in the CMB. Future missions will continue to study the blackbody radiation of the CMB. Advances in technology will allow for even more precise measurements. These missions aim to uncover finer details about the universe's early conditions and its subsequent evolution. Understanding blackbody radiation in the context of the CMB provides deep insights into the universe's thermal history. It connects the fundamental principles of physics with observational cosmology. This knowledge helps unravel the mysteries of the cosmos and our place within it. The Doppler effect is a change in frequency or wavelength of a wave in relation to an observer moving relative to the wave source. This effect is commonly observed with sound waves, such as the change in pitch of a passing siren. In cosmology, the Doppler effect also applies to light waves, influencing our understanding of the universe's expansion. Redshift is a specific manifestation of the Doppler effect for light. When an object in space moves away from us, its light waves stretch, shifting towards the red end of the spectrum. This phenomenon is known as redshift and provides crucial information about the motion and distance of celestial objects. Edwin Hubble's observation of redshifted light from distant galaxies was groundbreaking. It indicated that these galaxies are moving away from us, implying that the universe is expanding. This discovery was a pivotal piece of evidence for the Big Bang theory. In the context of the cosmic microwave background, redshift plays a significant role. As the universe expanded, the CMB photons were redshifted, stretching their wavelengths from the visible spectrum to the microwave range we observe today. This redshifting has cooled the CMB to its current temperature of 2.725 Kelvin. The Doppler effect also contributes to the anisotropies observed in the CMB. The motion of matter in the early universe caused variations in the observed temperature of the CMB. These Doppler shifts provide insights into the velocity and distribution of matter shortly after the Big Bang. The Sachs-Wolfe effect is another related phenomenon. It describes how gravitational redshift affects the CMB. Photons climbing out of gravitational wells lose energy, resulting in redshifted light, which contributes to the temperature fluctuations observed in the CMB. Redshift is not limited to the CMB, but is also observed in the light from galaxies and quasars. The extent of the redshift helps determine the distance and velocity of these objects. This information is crucial for mapping the large-scale structure of the universe. Cosmologists use redshift data to understand the rate of the universe's expansion, quantified by the Hubble constant. By measuring redshifts of distant galaxies and comparing them to their distances, scientists can refine the value of the Hubble constant, offering insights into the universe's expansion history. The study of redshift also aids in the detection and analysis of dark energy. Observations of redshifted light from distant supernovae have shown that the universe's expansion is accelerating. This acceleration is attributed to dark energy, a mysterious force driving the universe's growth. Redshift surveys, such as those conducted by the Sloan Digital Sky Survey, provide extensive data on the distribution of galaxies. These surveys map the large-scale structure of the universe, revealing patterns that inform our understanding of cosmic evolution and the influence of dark matter and dark energy. The Doppler effect and redshift are fundamental tools in the study of cosmology. They provide a window into the dynamics of the universe, from the motion of individual stars to the expansion of the cosmos itself. These concepts are integral to interpreting a wide range of astronomical observations. The discovery of cosmic redshift has transformed our understanding of the universe. It supports the notion that the universe had a beginning and has been expanding ever since. This expansion is a cornerstone of the Big Bang theory and continues to shape our view of the cosmos. Technological advancements have enhanced our ability to measure redshift with great precision. Instruments like spectrographs on telescopes can detect the subtle shifts in light from distant objects. These precise measurements are essential for studying the universe's expansion and its underlying causes. The interplay between the Doppler effect, redshift, and the CMB provides a comprehensive picture of the universe's history and structure. By studying these phenomena, scientists can trace the evolution of the cosmos from its earliest moments to its present state. As research continues, the Doppler effect and redshift will remain crucial in unveiling the mysteries of the universe. They offer insights into the fundamental forces shaping the cosmos and guide our quest to understand the nature of space, time, and everything within it. The Sachs-Wolfe effect is a critical phenomenon in cosmology related to the cosmic microwave background. It describes how variations in gravitational potential impact the temperature of CMB photons. These variations lead to observable anisotropies in the CMB. When CMB photons pass through regions of varying gravitational potential, they experience shifts in energy. Photons climbing out of gravitational wells lose energy, resulting in redshift. Conversely, photons falling into gravitational wells gain energy, resulting in blue shift. This effect causes temperature fluctuations in the CMB. Regions with deeper gravitational wells appear cooler because photons lose energy escaping these wells. Regions with shallower wells or peaks appear warmer due to the opposite effect. The Sachs-Wolfe effect can be divided into two components: the ordinary Sachs-Wolfe effect and the integrated Sachs-Wolfe effect. The ordinary Sachs-Wolfe effect occurs at the surface of last scattering, where photons decoupled from matter. The integrated Sachs-Wolfe effect occurs as photons travel through evolving gravitational potentials over time. The ordinary Sachs-Wolfe effect is most significant on large angular scales. It contributes to the temperature anisotropies observed in the CMB. By studying these anisotropies, scientists can infer the distribution of matter in the early universe. The integrated Sachs-Wolfe effect is sensitive to the evolution of cosmic structures. As the universe expands, gravitational potentials change, affecting the energy of passing photons. This effect provides insights into the nature of dark energy and the dynamics of cosmic expansion. Detection of the integrated Sachs-Wolfe effect offers evidence for dark energy. Observations show that large-scale gravitational potentials decay over time, consistent with an accelerating universe. This decay affects the CMB photons, leaving a distinct imprint that supports the existence of dark energy. The Sachs-Wolfe effect is closely linked to the large-scale structure of the universe. By analyzing the CMB, scientists can map the distribution of matter and gravitational potentials. This mapping helps understand how cosmic structures formed and evolved. Measurements of the Sachs-Wolfe effect require precise observations of the CMB. Satellites like COBE, WMAP, and Planck have provided detailed data on temperature fluctuations. These observations are crucial for studying the Sachs-Wolfe effect and its implications for cosmology. The effect also has implications for the study of primordial density fluctuations. The initial conditions of the universe left imprints in the form of gravitational potentials. By studying the Sachs-Wolfe effect, scientists can gain insights into these primordial fluctuations and the early universe's state. The ordinary Sachs-Wolfe effect helps constrain models of cosmic inflation. Inflation predicts specific patterns of density fluctuations that should be reflected in the gravitational potentials. Observing these patterns in the CMB supports inflationary models. The integrated Sachs-Wolfe effect can be observed by correlating CMB data with large-scale structure surveys. This correlation provides direct evidence of the impact of dark energy on cosmic evolution. It is a powerful tool for understanding the interplay between matter, radiation, and dark energy. The effect also influences the polarization of the CMB. Gravitational potentials can induce polarization patterns, providing additional data for analysis. Studying these patterns helps refine models of the universe's initial conditions and subsequent evolution. The Sachs-Wolfe effect underscores the interconnected nature of cosmological phenomena. It links the physics of the early universe with the large-scale structure observed today. This connection helps build a cohesive picture of cosmic history. Ongoing research continues to explore the Sachs-Wolfe effect in greater detail. Advances in observational technology and data analysis techniques promise to reveal new insights. Understanding this effect is crucial for unlocking the mysteries of dark energy, inflation, and the universe's ultimate fate. The Sachs-Wolfe effect remains a cornerstone of modern cosmology. Its study provides a deeper understanding of the universe's structure, evolution, and fundamental forces. As we continue to unravel its complexities, we gain a clearer picture of the cosmos and our place within it. The large-scale structure of the universe refers to the distribution of galaxies, clusters, and superclusters on scales of hundreds of millions of light-years. This structure reveals a complex cosmic web formed by gravitational forces acting over billions of years. Studying it helps us understand the processes that shaped the universe from its earliest moments. One key feature of the large-scale structure is the cosmic web. This web-like arrangement consists of dense nodes, where galaxy clusters reside, connected by filaments of galaxies and vast voids with few galaxies. This intricate pattern emerged from tiny density fluctuations in the early universe. The cosmic microwave background provides the initial conditions for this structure. The temperature fluctuations observed in the CMB correspond to density variations that eventually grew into galaxies and clusters. By mapping the CMB, we can trace the origins of the large-scale structure. Gravity played a crucial role in shaping the large-scale structure. Small initial density fluctuations grew over time due to gravitational attraction. Regions with slightly higher density attracted more matter, becoming the dense nodes of the cosmic web. Observations of galaxy redshifts have been instrumental in mapping the large-scale structure. Surveys like the Sloan Digital Sky Survey have catalogued the positions and velocities of millions of galaxies. This data reveals the three-dimensional distribution of matter in the universe. Dark matter is a critical component of the large-scale structure. Although it does not emit light, its gravitational effects are observable. Dark matter's presence is inferred from the motions of galaxies and the gravitational lensing of light from distant objects. Simulations of cosmic evolution help us understand the formation of the large-scale structure. These simulations use the laws of physics to model the growth of structures from initial density fluctuations. Comparing these models with observations helps refine our understanding of the universe's composition and dynamics. The large-scale structure provides evidence for dark energy. Observations show that the expansion of the universe is accelerating, driven by dark energy. This acceleration affects the growth of cosmic structures, leaving an imprint that can be observed in large-scale surveys. Baryon acoustic oscillations are another important feature of the large-scale structure. These oscillations are regular, periodic fluctuations in the density of visible matter. They provide a standard ruler for measuring cosmic distances and the expansion rate of the universe. The distribution of galaxies also reflects the history of cosmic inflation. Inflation predicts specific patterns in the initial density fluctuations. Observing these patterns in the large-scale structure supports the inflationary model of the early universe. The study of the large-scale structure involves multiple observational techniques. These include galaxy redshift surveys, gravitational lensing studies, and the analysis of the CMB. Each method provides different insights into the distribution and dynamics of matter. Gravitational lensing, the bending of light by massive objects, is particularly useful for studying dark matter. By observing how light from distant galaxies is distorted, scientists can map the distribution of dark matter in clusters and across the cosmic web. Understanding the large-scale structure helps answer fundamental questions about the universe's fate. The distribution and behavior of dark matter and dark energy influence whether the universe will continue expanding, slow down, or eventually collapse. The cosmic web is a dynamic structure, continually evolving over time. Galaxies merge, clusters grow, and voids expand. Studying these processes helps us understand the life cycle of cosmic structures and the forces shaping them. The large-scale structure is a testament to the universe's complexity and the power of gravity. It provides a bridge between the tiny fluctuations observed in the CMB and the vast cosmic formations we see today. Exploring this structure deepens our knowledge of the cosmos and the forces that govern it. Temperature fluctuations in the cosmic microwave background are essential for understanding the universe's early conditions. These tiny variations, on the order of 1 part in 100,000, reflect slight differences in density and temperature shortly after the Big Bang. They provide critical clues about the initial state of the universe. These fluctuations were first detected by the COBE satellite and later studied in greater detail by WMAP and Planck. The data collected by these missions reveal a detailed map of the temperature variations across the sky. These maps show how matter was distributed in the early universe. The temperature fluctuations are directly linked to the sound waves that propagated through the hot plasma of the early universe. Regions of higher density correspond to compressions, while lower density regions correspond to rarefactions. These sound waves left imprints in the form of temperature variations. Studying these fluctuations allows scientists to infer the physics of the early universe. The size and distribution of the temperature variations provide insights into the nature of the primordial fluctuations that seeded the formation of galaxies and clusters. These details help refine models of cosmic inflation. The power spectrum of the CMB describes how temperature fluctuations vary with scale. It shows a series of peaks and troughs that correspond to the different modes of sound waves in the early universe. The first peak, in particular, provides information about the overall geometry of the universe. The height and position of these peaks in the power spectrum are influenced by the universe's composition. They reveal the relative amounts of dark matter, dark energy, and ordinary matter. By analyzing the power spectrum, scientists can determine the proportions of these components. Temperature fluctuations also provide a way to measure the Hubble constant, the rate of the universe's expansion. By comparing the observed power spectrum with theoretical models, scientists can refine their estimates of the Hubble constant. This helps improve our understanding of the universe's expansion history. The detailed study of temperature fluctuations has confirmed the flatness of the universe. The observed pattern of fluctuations is consistent with a flat geometry, supporting the predictions of the inflationary model. This flatness has profound implications for the overall structure and fate of the universe. These fluctuations also reveal information about the reionization era. The interaction of CMB photons with free electrons during reionization affects the temperature fluctuations. By studying these effects, scientists can learn about the formation of the first stars and galaxies. Temperature fluctuations are not uniformly distributed, but show a characteristic pattern known as anisotropy. This anisotropy reflects the underlying distribution of matter and energy in the early universe. Analyzing these patterns helps scientists understand the large-scale structure of the cosmos. Polarization of the CMB is closely related to temperature fluctuations. The same processes that caused temperature variations also induced polarization in the CMB. Studying this polarization provides additional information about the early universe's conditions and the effects of cosmic inflation. Temperature fluctuations also offer insights into the Sachs-Wolfe effect, where gravitational potentials affect the energy of CMB photons. This effect creates additional anisotropies that can be observed and studied. It helps scientists understand the distribution of matter and gravitational potentials in the early universe. The analysis of temperature fluctuations involves sophisticated statistical techniques. Scientists use these methods to extract meaningful information from the data and to compare it with theoretical models. This process is essential for testing and refining our understanding of the universe. The ongoing study of temperature fluctuations continues to yield new discoveries. As observational technology improves, scientists can measure these fluctuations with greater precision and detail. These advancements help us uncover more about the universe's origins and its subsequent evolution. Understanding temperature fluctuations in the CMB is fundamental to cosmology. These tiny variations hold the key to unraveling the history and structure of the universe. By studying them, scientists gain deeper insights into the forces and processes that shape the cosmos. The polarization of the cosmic microwave background provides additional insight into the early universe. Polarization occurs when light waves oscillate in a preferred direction. For the CMB, this polarization was imprinted during the era of recombination. Thomson scattering, where CMB photons interact with free electrons, is the primary cause of this polarization. As photons scattered, they acquired a slight polarization. This effect depended on the temperature fluctuations and the motion of the plasma in the early universe. There are two types of polarization patterns observed in the CMB, E-mode and B-mode. E-mode polarization patterns are radial or circular and were first detected by the DAISY experiment. These patterns align with temperature fluctuations in the CMB. B-mode polarization patterns are more complex and can be caused by gravitational waves from the early universe. Detecting B-mode polarization provides evidence for inflation, as these patterns are expected to be imprinted by primordial gravitational waves. This detection is a major goal in modern cosmology. The Planck satellite made significant contributions to the study of CMB polarization. Its detailed measurements of E-mode polarization have refined our understanding of the universe's early conditions. Planck's data also provided hints of B-mode polarization, sparking further research. Polarization measurements help us understand the reionization era. When the first stars and galaxies formed, they reionized the universe, scattering CMB photons and imprinting additional polarization. Studying this polarization helps scientists learn about the formation of early cosmic structures. The polarization of the CMB is a powerful tool for testing cosmological models. By comparing observed polarization patterns with theoretical predictions, scientists can test the accuracy of models describing the early universe. This process helps refine our understanding of fundamental physics. The polarization data also provides insights into the distribution of matter and energy in the universe. Analyzing these patterns helps determine the amounts of dark matter and dark energy. This information is crucial for constructing accurate cosmological models. Instruments designed to measure CMB polarization must be highly sensitive and precise. They need to detect minute differences in the polarization of CMB photons. This requires advanced technology and careful calibration to ensure accurate measurements. Ground-based telescopes like the South Pole Telescope and the Atacama Cosmology Telescope also contributed to CMB polarization studies. These observatories are located in remote, high-altitude locations to minimize atmospheric interference. Their observations complement data from satellite missions. Future missions aim to improve the measurement of CMB polarization. Projects like the Simons Observatory and the CMB S4 experiment will provide even more detailed polarization maps. These missions will help answer key questions about the early universe and cosmic inflation. The study of CMB polarization is an evolving field. As technology advances, scientists can measure polarization with greater precision and accuracy. These improvements will lead to new discoveries about the universe's origins and evolution. Polarization patterns in the CMB are not only fascinating but also essential for understanding the universe. They provide a unique window into the conditions and processes that shape the cosmos. By studying polarization, we gain deeper insights into the fundamental nature of the universe. Understanding the polarization of the CMB helps connect theoretical physics with observational data. It allows scientists to test predictions of inflationary models and other cosmological theories. This connection enhances our overall understanding of the universe. The polarization of the cosmic microwave background remains a key focus in cosmological research. Its study continues to reveal new information about the early universe and the forces that shaped it. As we uncover more about CMB polarization, we move closer to answering some of the most profound questions in cosmology. B-mode polarization is a specific pattern in the cosmic microwave background that provides crucial evidence for cosmic inflation. Unlike the simpler E-mode polarization, B-mode patterns are more complex and can arise from two primary sources: gravitational lensing and primordial gravitational waves. Gravitational lensing is caused by massive structures bending the path of CMB photons. This lensing distorts the E-mode polarization, creating a faint B-mode pattern. This effect is well documented and provides valuable information about the distribution of matter in the universe. The more intriguing source of B-mode polarization is primordial gravitational waves. These waves, generated during the rapid expansion of the universe known as inflation, would have imprinted a distinct B-mode pattern in the CMB. Detecting this pattern would provide direct evidence for inflation. B-mode polarization patterns are swirly and differ from the radial or tangential patterns of E-modes. These distinct patterns make B-modes a clear signature of the processes that generated them. Observing these patterns requires extremely sensitive instruments due to their faintness. The first detection of B-mode polarization from gravitational lensing was made by the South Pole Telescope and the Atacama Cosmology Telescope. These observations confirmed the presence of lensing-induced B-modes, providing insights into the large-scale structure of the universe. Primordial B-modes, however, remain more elusive. Experiments like BICEP2 initially reported detection, but further analysis revealed that much of the signal could be attributed to foreground dust in our galaxy. This highlighted the challenges in distinguishing primordial signals from other sources. Despite these challenges, the search for primordial B-mode polarization continues. Instruments are being refined, and new experiments are being designed to improve sensitivity and accuracy. Detecting primordial B-modes would be a groundbreaking achievement in cosmology. The detection of primordial B-modes would have profound implications. It would provide direct evidence for the inflationary period of the early universe. This discovery would help validate models of inflation and provide insights into the physics of the universe at incredibly high energies. B-mode polarization also helps in understanding the reionization era. The scattering of CMB photons by free electrons during reionization can generate B-mode patterns. Studying these patterns provides information about the timing and process of reionization. Future missions like the Simons Observatory and CMB S4 aim to detect B-mode polarization with greater precision. These missions will deploy advanced technology to minimize noise and improve measurement accuracy. Their findings will be crucial for advancing our understanding of the early universe. The study of B-mode polarization is a testament to the intersection of theory and observation in cosmology. Theoretical predictions about inflation and gravitational waves are being tested with increasingly sophisticated observational tools. This synergy drives the field forward. B-mode polarization patterns offer a unique window into the universe's infancy. They carry information about processes that occurred fractions of a second after the Big Bang. Understanding these patterns helps reconstruct the universe's early history. The ongoing efforts to detect B-mode polarization exemplify the scientific method. Hypotheses about the early universe are rigorously tested through observation and analysis. This iterative process gradually unveils the universe's deepest secrets. B-mode polarization remains a frontier in cosmological research. Each step towards detecting and understanding these patterns brings us closer to confirming key aspects of our cosmological models. The pursuit of this knowledge continues to inspire advancements in both theory and technology. As research progresses, B-mode polarization will likely provide even more profound insights. The study of these patterns is essential for piecing together the complete story of the universe's origins. This endeavor continues to shape our understanding of the cosmos and its fundamental laws. The implications of B-mode polarization for cosmology are profound. Detecting these patterns would provide direct evidence for the theory of cosmic inflation. This would confirm that the universe underwent a rapid expansion shortly after the Big Bang. Understanding B-mode polarization helps refine our models of the early universe. It provides insights into the conditions and processes that occurred during inflation. This information is crucial for developing accurate and comprehensive cosmological theories. B-mode polarization also offers a way to probe fundamental physics at extremely high energies. The patterns imprinted by primordial gravitational waves are linked to energy scales far beyond those accessible by particle accelerators. Studying these patterns can reveal new aspects of fundamental forces and particles. The detection of B-mode polarization would support the existence of gravitational waves predicted by Einstein's theory of general relativity. This would be a major validation of our understanding of gravity. It would also open up new avenues for studying the universe through gravitational wave astronomy. Implications for dark matter research are significant as well. B-mode polarization data can help map the distribution of dark matter. This mapping is crucial for understanding how dark matter influences the formation and evolution of cosmic structures. B-mode polarization measurements contribute to the study of dark energy. By providing detailed information about the universe's expansion, these measurements help constrain models of dark energy. Understanding dark energy is essential for predicting the ultimate fate of the universe. The study of B-mode polarization enhances our knowledge of the Rayonization era. By analyzing the effects of Rayonization on the CMB, scientists can learn about the formation of the first stars and galaxies. This period is critical for understanding the universe's transition from darkness to light. B-mode polarization also helps improve the accuracy of cosmological parameters. Precise measurements of these patterns refine estimates of the Hubble constant and other key parameters. This leads to a better understanding of the universe's expansion history and overall dynamics. The implications for the large-scale structure of the universe are profound. B-mode polarization data provides a clearer picture of how cosmic structures formed and evolved. This information helps test and validate models of structure formation and growth. Detecting B-mode polarization can reveal new aspects of inflationary models. Different models predict varying strengths and patterns of B-mode signals. Observations can help distinguish between competing theories, guiding the development of more accurate models. B-mode polarization studies can also inform theories of quantum gravity. The conditions during inflation are closely linked to quantum gravitational effects. Observing B-mode patterns provides indirect evidence for these effects, helping bridge the gap between quantum mechanics and general relativity. The pursuit of B-mode polarization detection drives technological innovation. Developing highly sensitive instruments and advanced analysis techniques pushes the boundaries of observational cosmology. These advancements have broader applications in other areas of science and technology. B-mode polarization research fosters international collaboration. Scientists and institutions around the world work together on experiments and missions. This collaboration enhances the exchange of ideas and resources, accelerating progress in cosmological research. The study of B-mode polarization enriches our understanding of the universe's origins. It connects the earliest moments of the cosmos with its large-scale structure. This connection helps build a coherent narrative of cosmic history from the Big Bang to the present. Ultimately, the implications of B-mode polarization for cosmology underscore the dynamic and evolving nature of the field. Each discovery leads to new questions and challenges, driving the continuous quest for knowledge. The study of these patterns is a vital part of our journey to understand the universe and our place within it. Methods of calculating the universe's age involve several key techniques. One of the primary methods is through observations of the cosmic microwave background. By studying the temperature fluctuations and the expansion rate encoded in the CMB, scientists can estimate the universe's age with high precision. The Hubble constant is another crucial factor in determining the age of the universe. It measures the rate at which the universe is expanding. By observing distant galaxies and their redshifts, astronomers can calculate this constant and use it to estimate the time elapsed since the Big Bang. Another method involves studying the oldest known star clusters, particularly globular clusters. These clusters contain some of the oldest stars in the universe. By determining the age of these stars, scientists can establish a lower limit for the age of the universe. White dwarf cooling is another technique used to estimate the universe's age. White dwarfs are the remnants of low-mass stars that have exhausted their nuclear fuel. By studying the cooling rates of white dwarfs in globular clusters, astronomers can infer their ages and, consequently, the age of the universe. Nuclear cosmochronology is a method that involves studying the abundance of radioactive isotopes in old stars. By measuring the ratios of these isotopes, scientists can estimate the time since these elements were formed, providing another way to calculate the universe's age. Observations of distant supernovae also contribute to age calculations. Type Ia supernovae, in particular, serve as standard candles for measuring cosmic distances. By studying their brightness and redshift, astronomers can infer the expansion history of the universe. Another important method is through the study of baryon acoustic oscillations. These periodic density fluctuations in the early universe left imprints in the large-scale structure of the cosmos. By measuring the scale of these oscillations, scientists can determine the expansion rate and estimate the universe's age. The age of the universe can also be inferred from the chemical abundances observed in old stars. The ratios of certain elements, such as uranium to thorium, provide clocks that can be used to estimate stellar ages. This method helps cross-check other age determination techniques. The study of the large-scale structure of the universe provides another way to estimate its age. By mapping the distribution of galaxies and clusters and comparing these maps with simulations, scientists can infer the history and timeline of cosmic evolution. Cosmic chronometers, such as the ages of galaxy populations, offer additional age estimates. By studying the stellar populations in galaxies at different redshifts, astronomers can piece together the timeline of galaxy formation and evolution, providing clues to the universe's overall age. Gravitational lensing is another method that indirectly contributes to age calculations. By studying the bending of light from distant objects by massive structures, scientists can infer the mass distribution of the universe, which helps refine models of its expansion history. The combination of these various methods provides a comprehensive approach to estimating the universe's age. Each technique offers unique insights and helps cross-verify the results from other methods. This multifaceted approach ensures more accurate and reliable age estimates. Technological advancements continue to improve the precision of age measurements. Instruments on ground-based telescopes and space observatories are constantly being refined. These advancements enable more detailed observations and more accurate calculations of the universe's age. Collaboration between different scientific disciplines also enhances our understanding of the universe's age. Cosmologists, astronomers, and physicists work together to integrate data from various sources. This collaborative effort helps build a coherent and consistent picture of cosmic history. Ultimately, calculating the universe's age is a complex and ongoing endeavor. Each new discovery and technological advancement brings us closer to a more precise understanding. This pursuit not only helps us grasp the timeline of the cosmos, but also deepens our knowledge of the fundamental forces and processes that have shaped it. The cosmic microwave background plays a crucial role in determining the age of the universe. By analyzing the CMB, scientists can infer the conditions of the early universe and how it has evolved over time. The precise measurements of the CMB provide key data for these calculations. The temperature fluctuations in the CMB are directly linked to the density variations in the early universe. These fluctuations help scientists understand the rate of expansion, which is vital for determining the age. The expansion rate informs us how long the universe has been growing since the Big Bang. Another essential aspect is the measurement of the Hubble constant from the CMB data. This constant describes the current rate of expansion of the universe. By combining this with the CMB observations, scientists can backtrack to estimate the time elapsed since the Big Bang. The CMB also reveals information about the matter and energy content of the universe. Knowing the proportions of dark matter, dark energy, and ordinary matter helps refine age calculations. The balance of these components affects the universe's expansion history. The detailed power spectrum of the CMB provides insights into the geometry of the universe. A flat universe, as indicated by the CMB data, supports specific models of cosmic inflation. These models help scientists calculate the universe's age more accurately. Polarization patterns in the CMB also contribute to age determination. The E-mode and B-mode polarizations provide information about the early universe's conditions. Studying these patterns helps refine estimates of how long the universe has been expanding. The Sachs-Wolfe effect, observed in the CMB, is another piece of the puzzle. This effect, caused by gravitational redshift, impacts the temperature fluctuations. Analyzing the Sachs-Wolfe effect helps scientists understand the universe's large-scale structure and its expansion history. Gravitational lensing of the CMB adds another layer of data. The way CMB photons are bent by massive structures provides information about the distribution of matter. This data helps refine models of cosmic evolution and, consequently, the age of the universe. The era of recombination, when the CMB was released, marks a specific point in the universe's timeline. By studying the conditions at recombination, scientists can set a lower limit for the age of the universe. This helps anchor other age estimates. The CMB also provides a cross-check for other methods of age determination. By comparing CMB-based estimates with those from star clusters or radioactive decay, scientists can verify their accuracy. Consistent results from different methods increase confidence in the calculated age. Advanced statistical methods are used to analyze CMB data. Techniques such as Bayesian inference and maximum likelihood estimation help refine age estimates. These methods integrate CMB observations with theoretical models to produce precise results. The CMB data continues to improve with new missions and technology. Each new set of observations provides more detailed and accurate information. This ongoing refinement helps continually update and improve the age estimates of the universe. Collaborative efforts in the scientific community enhance the role of the CMB in age determination. Data sharing and joint analysis projects bring together expertise from around the world. This collective effort ensures the most accurate and comprehensive understanding. The precise role of the CMB in determining the universe's age highlights its importance in cosmology. It provides a fundamental benchmark for all other methods. Understanding the CMB is key to piecing together the entire timeline of the cosmos. Ultimately, the CMB offers a unique and powerful tool for understanding the universe's history. Its detailed data allows scientists to accurately estimate the age of the universe. This insight helps us comprehend the broader context of cosmic evolution and our place within it. The age of the universe estimated from the cosmic microwave background can be compared with other methods. One common method is the study of globular clusters, which contain some of the oldest stars in the universe. By determining the ages of these stars, astronomers can set a minimum age for the universe. White dwarf cooling rates offer another approach. White dwarfs are remnants of ancient stars, and their cooling process can be precisely measured. By analyzing the cooling rates, scientists can estimate the time since these stars formed, providing another age benchmark. Radioactive decay in stars also serves as a cosmic clock. Elements like uranium and thorium decay at known rates, and their ratios in old stars can be used to estimate ages. This method helps cross-check the age derived from the CMB. Type Ia supernovae are used as standard candles to measure cosmic distances. Observing these supernovae at different redshifts helps determine the expansion rate of the universe. This rate, combined with distance measurements, provides an estimate of the universe's age. Baryon acoustic oscillations are another tool. These oscillations are imprints from the early universe visible in the large-scale structure of galaxies. Measuring the scale of these oscillations helps determine the rate of expansion and the age of the universe. The Hubble constant derived from various observations is crucial for age calculations. Different methods provide different values, leading to the so-called Hubble tension. Comparing these values with the CMB-derived Hubble constant helps refine the universe's age estimate. Chemical abundances in old stars also provide age estimates. By studying the ratios of long-lived radioactive isotopes, scientists can infer the time since these elements were formed. This method complements other age determination techniques. Cosmic chronometers such as galaxy population ages offer additional insights. By studying the stellar populations in galaxies at various redshifts, astronomers can piece together a timeline of galaxy formation and evolution. This helps estimate the age of the universe. Gravitational lensing, which bends light from distant objects, can be used to measure mass distribution. By studying the lensing effects, scientists can infer the universe's structure and history, contributing to age estimates. The consistency of age estimates from different methods strengthens the reliability of the calculated age. When multiple methods converge on the same value, it increases confidence in the results. This cross-validation is crucial for robust cosmological conclusions. Technological advancements continue to improve the precision of all these methods. As instruments become more sensitive and data analysis techniques more sophisticated, age estimates become more accurate. This ongoing improvement helps refine our understanding of the universe's timeline. Collaboration across different scientific fields enhances the accuracy of age estimates. Astronomers, physicists, and cosmologists work together, sharing data and methods. This interdisciplinary approach leads to a more comprehensive understanding of the universe's age. Discrepancies between different age estimates, such as the Hubble tension, drive further research. Resolving these discrepancies can lead to new discoveries about the universe's expansion and fundamental properties. These challenges push the boundaries of our knowledge. Ultimately, comparing age estimates from various methods provides a holistic view of the universe's timeline. Each method offers unique insights, and together they build a coherent picture. This comprehensive approach is essential for understanding the history and evolution of the cosmos. Uncertainties and challenges are inherent in estimating the age of the universe. One significant challenge is the precise measurement of the Hubble constant. Different methods yield slightly different values, leading to ongoing debates and refinements in age calculations. The Hubble tension, or the discrepancy between Hubble constant values from different observations, is a major source of uncertainty. This tension suggests there may be unknown factors influencing our measurements or understanding of cosmic expansion. Calibrating distance measurements accurately is another challenge. The distances to astronomical objects must be known precisely to determine the expansion rate. Any errors in these measurements can significantly impact the estimated age of the universe. Foreground contamination in CMB data presents additional difficulties. Emissions from our galaxy and other sources can obscure the true CMB signal. Removing this contamination requires advanced algorithms and precise data processing techniques. The modeling of dark energy and dark matter also introduces uncertainties. These components make up the majority of the universe, but their exact properties and behaviors are not fully understood. Variations in their models can affect age estimates. Cosmic variance, or the statistical variation in observations of the universe, can influence results. This natural variation must be accounted for when analyzing CMB data and other measurements. It adds a layer of complexity to age determination. The initial conditions of the universe, such as the exact nature of the inflationary period, are not completely known. Assumptions about these conditions affect the interpretation of CMB data and the calculated age of the universe. The precision of current instruments, while advanced, still has limits. Future technological improvements are needed to reduce measurement errors further. Enhanced sensitivity and resolution will help refine age estimates, and resolve existing uncertainties. Theoretical models of cosmic evolution are continually being tested and refined. Discrepancies between models and observations can highlight gaps in our understanding. Addressing these gaps is crucial for improving the accuracy of age determinations. Gravitational lensing introduces additional complexities. While it provides valuable information, interpreting lensing effects requires precise knowledge of the mass distribution in the universe. Any errors in these models can affect age estimates. Cross-checking different methods for consistency is essential but challenging. Each method has its own sources of error and assumptions. Ensuring that all methods align requires rigorous analysis and careful consideration of potential biases. The influence of unknown or poorly understood physical processes remains a potential source of uncertainty. New discoveries in physics could reveal factors that significantly impact our measurements and models. Staying open to these possibilities is crucial for accurate age determination. The cosmic microwave background itself, while providing a wealth of information, has limitations. The data is a snapshot from a specific period in the universe's history. Interpreting this data accurately requires understanding the full context of cosmic evolution. Interdisciplinary collaboration helps address these challenges. By combining expertise from different fields, scientists can develop more robust methods and models. This collaborative approach is vital for overcoming the complexities of age determination. Ongoing research and advancements in technology promise to reduce these uncertainties over time. As our understanding of the universe deepens, the precision of age estimates will improve. This continuous progress is key to unlocking the full history of the cosmos. Accurate age determination of the universe is fundamental to cosmology. It helps us understand the timeline of cosmic events from the Big Bang to the present. This timeline is crucial for studying the formation and evolution of galaxies, stars, and other cosmic structures. Knowing the age of the universe allows scientists to test and refine theoretical models. These models describe the behavior of matter and energy over billions of years. Accurate age estimates help validate these models and ensure they align with observational data. The age of the universe also provides context for other astronomical measurements. It helps place observations of distant objects into a broader framework. This context is essential for understanding the history and development of the cosmos. Accurate age determination helps resolve fundamental questions about the nature of the universe. It sheds light on the initial conditions and the processes that have shaped the universe. This understanding is crucial for unraveling the mysteries of dark matter and dark energy. The precision of age estimates impacts our knowledge of cosmic expansion. Accurate measurements of the universe's age help determine the rate at which the universe is expanding. This rate, quantified by the Hubble constant, is a key parameter in cosmology. Age determination influences our understanding of the early universe. It provides insights into periods like cosmic inflation and the era of recombination. Accurate age estimates help refine our knowledge of these critical phases. The age of the universe is also important for understanding the life cycle of stars and galaxies. It helps scientists trace the formation and evolution of these objects over time. This information is vital for constructing accurate models of stellar and galactic evolution. Accurate age estimates help address the Hubble tension. By refining the age and expansion rate of the universe, scientists can better understand the discrepancies between different measurements. Resolving this tension is crucial for a coherent picture of cosmic expansion. The age of the universe provides a benchmark for studying cosmic structures. It helps determine when various structures, such as galaxy clusters, formed. This benchmark is essential for understanding the growth and development of large-scale structures. Understanding the age of the universe aids in exploring the nature of dark energy. Accurate age estimates provide constraints on the properties of dark energy. These constraints are vital for developing theories about this mysterious force driving cosmic acceleration. Accurate age determination impacts our understanding of the ultimate fate of the universe. It helps predict whether the universe will continue to expand, slow down, or eventually collapse. This prediction is fundamental for studying the long-term evolution of the cosmos. The precision of age estimates informs the study of primordial nucleosynthesis. It helps validate models of element formation in the early universe. This validation is crucial for understanding the abundance of elements observed today. Accurate age estimates enhance interdisciplinary research. They provide a common framework for astronomers, physicists, and cosmologists. This framework facilitates collaboration and the integration of data from various fields. The pursuit of accurate age determination drives technological innovation. It leads to the development of advanced instruments and data analysis techniques. These innovations have broad applications beyond cosmology, benefiting other scientific disciplines. Ultimately, accurate age determination deepens our understanding of the universe and our place within it. It connects the dots between various cosmic phenomena, creating a cohesive narrative of the cosmos. This understanding enriches our knowledge and inspires further exploration. Matter, dark matter, and dark energy are the three primary components of the universe. Ordinary matter, which makes up about 5% of the universe, includes everything we can see and touch. This encompasses stars, planets, galaxies, and all the atoms that form these structures. Dark matter, on the other hand, accounts for about 27% of the universe. It does not emit, absorb, or reflect light, making it invisible to current instruments. However, its presence is inferred from gravitational effects on visible matter and the structure of the universe. Dark energy is the most mysterious component, constituting roughly 68% of the universe. It is believed to be responsible for the accelerated expansion of the universe. Unlike dark matter, dark energy is thought to have a repulsive effect, counteracting gravity. The study of these components helps scientists understand the overall structure and evolution of the universe. Observations of galaxy rotations and cosmic structures reveal the influence of dark matter. Without it, galaxies would not have enough gravitational pull to hold themselves together. Dark matter's presence is also detected through gravitational lensing. This phenomenon occurs when massive objects bend light from distant sources, magnifying and distorting their appearance. The amount of lensing observed can indicate the amount of dark matter present. Dark energy's effects are observed through the accelerated expansion of the universe. Type Ia supernovae, used as standard candles, show that distant galaxies are moving away from us at increasing speeds. This discovery has profound implications for our understanding of the cosmos. The cosmic microwave background provides additional evidence for dark matter and dark energy. The patterns observed in the CMB are influenced by the amounts and properties of these components. Analyzing these patterns helps refine our models of the universe. Understanding the interplay between matter, and dark energy is crucial for cosmology. These components interact to shape the large-scale structure of the universe. Their relative proportions affect the formation and evolution of galaxies, clusters, and other cosmic structures. Dark matter is believed to consist of unknown particles that interact weakly with ordinary matter. Many experiments aim to detect these particles directly, though none have yet succeeded. Discovering the nature of dark matter would be a major breakthrough in physics. Dark energy, though even less understood, is often modeled as a property of space itself. Some theories propose it is a new kind of field or energy intrinsic to space. Understanding dark energy could revolutionize our knowledge of fundamental physics. The lambda CDM model is the standard model of cosmology that includes dark matter and dark energy. This model accurately describes many observed features of the universe, from the CMB to the distribution of galaxies. It provides a framework for interpreting a wide range of cosmological data. Research into dark matter and dark energy is ongoing, with new observations and experiments continuously refining our understanding. Future missions, such as the James Webb Space Telescope and the Euclid satellite, aim to provide more data on these mysterious components. The discovery of dark matter and dark energy has transformed our view of the universe. They highlight how much remains unknown about the cosmos. Their study not only seeks to answer fundamental questions, but also opens up new avenues for scientific exploration. Collaboration across various scientific disciplines is essential to studying dark matter and dark energy. Physicists, astronomers, and cosmologists work together to develop theories and interpret data. This interdisciplinary approach is crucial for making progress in understanding the universe. Ultimately, the exploration of matter, and dark energy continues to push the boundaries of science. It challenges our understanding of the universe and inspires new technological and theoretical advancements. This ongoing journey is essential for uncovering the deepest mysteries of the cosmos. The cosmic microwave background has been crucial in understanding the composition of the universe. It provides a snapshot of the universe when it was just 380,000 years old. This snapshot reveals the distribution of matter and energy at that time. Analyzing the CMB's temperature fluctuations helps scientists determine the relative amounts of ordinary matter, and dark energy. These fluctuations are influenced by the density and distribution of these components. This information helps refine models of the universe's composition. The power spectrum of the CMB is a key tool in this analysis. It shows how temperature variations vary with scale. By examining the peaks and troughs in the power spectrum, scientists can infer the proportions of different types of matter and energy. The first peak in the power spectrum is particularly informative. It provides evidence for the amount of ordinary matter in the universe. This peak is influenced by the density of baryons, the building blocks of ordinary matter. Subsequent peaks in the power spectrum reveal the presence of dark matter. These peaks are shaped by the gravitational effects of dark matter on the early universe. The positions and heights of these peaks help determine the amount of dark matter. The overall shape of the power spectrum also provides evidence for dark energy. Dark energy affects the rate of the universe's expansion. By analyzing how this expansion has influenced the CMB, scientists can estimate the amount of dark energy. Polarization patterns in the CMB add another layer of information. These patterns are influenced by the interaction of CMB photons with matter. Studying these patterns helps scientists refine their estimates of the universe's composition. The Sachs-Wolfe effect observed in the CMB also contributes to our understanding of composition. This effect, caused by variations in gravitational potential, impacts the temperature fluctuations. Analyzing these fluctuations helps understand the distribution of matter in the early universe. Gravitational lensing of the CMB provides further insights. The way CMB photons are bent by massive structures helps map the distribution of dark matter. This data complements other observations and refines models of the universe's composition. The era of recombination, when the CMB was released, marks a specific point in the universe's history. Studying the conditions at recombination helps set constraints on the amounts of ordinary matter and dark matter. This period provides a crucial reference for understanding the universe's composition. The CMB also provides a cross-check for other measurements of cosmic composition. By comparing CMB data with observations from galaxy surveys and supernova studies, scientists can verify their estimates. Consistent results from different methods increase confidence in the calculated composition. Advancements in technology and data analysis techniques continue to improve our understanding of the CMB. Each new generation of instruments provides more detailed and accurate data. This ongoing refinement helps scientists make more precise estimates of the universe's composition. International collaborations enhance the study of the CMB and its contribution to understanding cosmic composition. Scientists from around the world share data and insights, improving the accuracy and reliability of their findings. This collaborative effort is crucial for advancing our knowledge. The study of the CMB has revolutionized our understanding of the universe. It has revealed the dominance of dark matter and dark energy, components that were unknown just a few decades ago. This discovery has transformed cosmology and opened up new fields of research. Ultimately, the CMB remains a cornerstone of modern cosmology. Its detailed data provides a foundation for understanding the universe's composition and evolution. The ongoing study of the CMB continues to yield new insights, driving our quest to understand the cosmos. Evidence from the cosmic microwave background strongly supports the existence of dark matter. The detailed patterns of temperature fluctuations in the CMB reveal the influence of dark matter on the early universe. These fluctuations are shaped by the gravitational effects of dark matter. The power spectrum of the CMB provides key insights into dark matter. The positions and heights of the peaks in the power spectrum are influenced by the amount of dark matter. The second and third peaks in particular are sensitive to the density of dark matter. Dark matter affects the rate of growth of density fluctuations in the early universe. By comparing the observed CMB fluctuations with theoretical models, scientists can estimate the amount of dark matter required to match observations. This comparison shows that dark matter is necessary to explain the observed patterns. The gravitational effects of dark matter help form the large-scale structure of the universe. Without dark matter, the observed distribution of galaxies and clusters would not be possible. The CMB provides a snapshot of the initial conditions that led to this structure. Gravitational lensing of the CMB offers additional evidence for dark matter. The way CMB photons are bent by massive structures reveals the presence of unseen mass. This lensing effect is consistent with the distribution of dark matter predicted by cosmological models. The Sachs-Wolfe effect also supports the existence of dark matter. This effect, caused by variations in gravitational potential, creates temperature fluctuations in the CMB. The observed fluctuations match the predictions of models that include dark matter. The CMB data helps constrain the properties of dark matter. By analyzing the CMB, scientists can infer the particle properties and behavior of dark matter. This information is crucial for developing and testing theories about the nature of dark matter. Dark matter's presence is also indicated by the overall density of the universe. The CMB data shows that the total density of matter is much higher than the density of ordinary matter alone. This discrepancy points to the existence of dark matter. The consistency between CMB observations and other measurements reinforces the evidence for dark matter. Galaxy rotation curves, galaxy cluster dynamics, and large-scale structure studies all point to the presence of dark matter. The CMB data provides a crucial piece of this puzzle. The lambda CDM model, which includes dark matter, accurately describes the CMB observations. This model explains the observed power spectrum and the distribution of temperature fluctuations. The success of this model supports the existence of dark matter. Dark matter's role in the formation of the first galaxies is also evident in the CMB. The initial density fluctuations amplified by dark matter provided the seeds for galaxy formation. The CMB data captures these early fluctuations, offering insights into the role of dark matter. The study of the CMB has led to predictions about the distribution of dark matter. Observations of the CMB align with these predictions, confirming the presence and distribution of dark matter in the universe. This alignment strengthens the case for dark matter's existence. The Planck satellite has provided the most detailed measurements of the CMB, further confirming the presence of dark matter. The data from Planck has refined our understanding of the amount and distribution of dark matter. This high-precision data is crucial for cosmological models. Future missions aim to provide even more detailed observations of the CMB. These missions will continue to refine our understanding of dark matter and its role in the universe. As technology advances, our ability to detect and study dark matter will improve. In summary, the CMB provides compelling evidence for dark matter. Its influence on the temperature fluctuations, power spectrum, and gravitational effects observed in the CMB supports its existence. The ongoing study of the CMB continues to reveal new insights into the nature of dark matter and its role in the cosmos. The cosmic microwave background also plays a crucial role in studying dark energy. Dark energy is the mysterious force driving the accelerated expansion of the universe. By analyzing the CMB, scientists can gain insights into the properties and effects of dark energy. The CMB provides a snapshot of the early universe, allowing us to trace the expansion history. By comparing the observed CMB data with theoretical models, scientists can infer the influence of dark energy on the universe's expansion. This helps to constrain the properties of dark energy. One key piece of evidence comes from the integrated Sachs-Wolfe effect. This effect occurs when CMB photons pass through changing gravitational potentials, influenced by dark energy. The observed temperature fluctuations in the CMB due to this effect provide information about the rate of expansion and the nature of dark energy. The overall geometry of the universe, as revealed by the CMB, also provides clues about dark energy. The CMB data indicates that the universe is flat, consistent with a significant amount of dark energy. This flatness is an important piece of evidence supporting the existence of dark energy. Dark energy affects the growth rate of cosmic structures. The CMB provides the initial conditions for this growth, allowing scientists to study how structures have evolved over time. By comparing these observations with models, the influence of dark energy on structure formation can be inferred. The CMB helps refine measurements of the Hubble constant, the rate at which the universe is expanding. Accurate values for the Hubble constant are essential for understanding dark energy. Discrepancies in these measurements, known as the Hubble tension, highlight the need for a deeper understanding of dark energy. Polarization patterns in the CMB also provide insights into dark energy. The polarization data helps to refine models of cosmic inflation and the subsequent expansion. These models are crucial for understanding the overall influence of dark energy. The study of baryon acoustic oscillations in the CMB contributes to our knowledge of dark energy. These oscillations provide a standard ruler for measuring cosmic distances and the expansion rate. Analyzing these patterns helps scientists understand the role of dark energy in the universe's history. Gravitational lensing observed in the CMB is influenced by dark energy. The way light is bent by massive structures provides information about the distribution of dark energy. This data helps refine models of the universe's expansion and the properties of dark energy. Future CMB missions aim to provide even more detailed data on dark energy. These missions will improve the precision of measurements and help resolve existing discrepancies. Advanced technology and new observations will deepen our understanding of dark energy. Collaboration between different fields of study enhances our understanding of dark energy. Cosmologists, physicists, and astronomers work together to interpret CMB data and develop models. This interdisciplinary approach is crucial for making progress in the study of dark energy. The role of dark energy in the universe's fate is a fundamental question in cosmology. The CMB provides essential data for predicting whether the universe will continue to expand, slow down, or eventually collapse. Understanding dark energy is key to answering this question. The influence of dark energy on the CMB also helps test alternative theories of gravity. By comparing observations with predictions from various theories, scientists can refine their understanding of fundamental forces. This process is essential for advancing theoretical physics. In summary, the CMB is a vital tool for studying dark energy. Its detailed data provides insights into the expansion history, the geometry of the universe, and the growth of cosmic structures. Ongoing research and future missions will continue to uncover the mysteries of dark energy and its role in the cosmos. Current models and theories in cosmology aim to explain the nature and behavior of the universe. The lambda cold dark matter model, or lambda CDM, is the standard model. It includes both dark matter and dark energy, providing a comprehensive framework for understanding cosmic evolution. Lambda CDM assumes a flat universe dominated by dark energy, accounting for about 68% of the total energy density. Dark matter makes up around 27%, while ordinary matter constitutes about 5%. This model successfully describes the observed large-scale structure and the cosmic microwave background. Cosmic inflation is a key component of modern cosmological theories. It posits that the universe underwent a rapid expansion shortly after the Big Bang. This theory explains the observed uniformity of the CMB and the large-scale structure of the universe. Inflationary models predict specific patterns in the CMB's temperature fluctuations. These predictions have been confirmed by observations from COBE, WMAP, and Planck. The consistency between theory and observation strengthens the case for cosmic inflation. Dark matter is modeled as a type of matter that interacts weakly with ordinary matter and radiation. Various candidates for dark matter particles include weakly interacting massive particles, WIMPs, and axions. Detecting these particles directly remains a significant challenge. Dark energy is often modeled as a cosmological constant, represented by lambda in the lambda CDM model. This constant provides a simple explanation for the accelerated expansion of the universe. Alternative theories propose that dark energy could be a dynamic field, such as quintessence. Theories of modified gravity offer alternative explanations to dark matter and dark energy. These theories suggest that changes to our understanding of gravity could account for cosmic observations. Examples include modified Newtonian dynamics, MOND, and tensor vector scalar gravity, TVES. Baryon acoustic oscillations, BAO, are a critical feature in cosmological models. These oscillations are relics from the early universe, imprinted in the distribution of galaxies. Measuring BAO helps refine our understanding of the expansion history and the properties of dark energy. Neutrinos, once thought to be massless, are now known to have a small mass. This discovery has implications for cosmology, as neutrinos contribute to the overall matter content of the universe. Understanding their role helps refine cosmological models. The study of primordial gravitational waves is a frontier in cosmology. These waves, predicted by inflationary theories, would leave specific imprints in the CMB's polarization. Detecting these imprints would provide strong evidence for inflation and offer insights into the physics of the early universe. The large-scale structure LSS of the universe is another focus of current models. LSS refers to the distribution of galaxies, clusters, and voids on cosmic scales. Understanding the formation and evolution of these structures is crucial for testing cosmological theories. Quantum cosmology seeks to understand the universe's origins through the principles of quantum mechanics. Theories like loop quantum gravity and string theory aim to describe the conditions at the very beginning of the universe. These theories could potentially unify general relativity and quantum mechanics. Observational cosmology continues to test and refine these models. New data from telescopes and satellites provide increasingly detailed observations of the universe. These observations are essential for validating and improving theoretical models. The search for dark matter particles involves both direct and indirect detection methods. Experiments like the Large Hadron Collider and underground detectors aim to find evidence of dark matter. Success in these efforts would have profound implications for cosmology. Future missions and experiments will continue to explore these models and theories. Projects like the James Webb Space Telescope and the Euclid satellite aim to provide new data on dark matter, dark energy, and the early universe. These efforts will help refine our understanding of the cosmos. The cosmic microwave background data, while incredibly informative, does have its limitations. One major limitation is the cosmic variance, which refers to the statistical uncertainty inherent in observations of the universe at large scales. This variance limits the precision with which we can measure certain properties of the universe. Foreground contamination is another significant challenge. Emissions from our galaxy, such as from dust and gas, can obscure the CMB signal. Removing this contamination requires complex modeling and can introduce uncertainties into the data. The CMB provides a snapshot of the universe at a specific time, around 380,000 years after the Big Bang. While this snapshot is crucial, it doesn't provide direct information about earlier periods, such as the first moments of the universe, or the era of inflation. Instrumental noise and calibration errors also impact the quality of CMB data. Even with advanced technology, measurements are never perfect, and any noise or errors must be carefully accounted for in the analysis. The resolution of CMB maps is limited by the capabilities of the observing instruments. While missions like Planck have provided high-resolution maps, future improvements are needed to capture even finer details of the CMB. Gravitational lensing of the CMB, while providing valuable information, can also complicate data interpretation. This lensing distorts the CMB signal, making it more challenging to extract accurate information about the early universe. B-mode polarization, which could provide evidence for primordial gravitational waves, is incredibly faint and difficult to detect. This makes it challenging to confirm theories of cosmic inflation and requires extremely sensitive instruments. Interpreting CMB data relies heavily on theoretical models. These models, while well supported, involve assumptions that may not fully capture the complexities of the universe. Any limitations or inaccuracies in these models can affect the conclusions drawn from CMB data. The CMB does not provide direct information about the nature of dark matter and dark energy. While it helps constrain their properties, understanding these mysterious components requires complementary observations and experiments. The CMB data is also limited by our understanding of fundamental physics. New discoveries in particle physics or quantum mechanics could change the interpretation of CMB observations, highlighting the need for continuous advancements in theoretical physics. Cosmic rays and other high-energy particles can interfere with CMB measurements. These particles can introduce additional noise and require sophisticated techniques to filter out their effects, adding complexity to the data analysis process. The vast amount of data collected from CMB observations requires extensive computational resources for analysis. Processing this data involves significant time and effort, and any limitations in computational power can affect the speed and accuracy of the analysis. CMB observations are primarily limited to the observable universe. They can't provide information about regions of the universe beyond our observational horizon, leaving certain aspects of the cosmos unexplored. Future missions to study the CMB will need to address these limitations. New technologies and methods are being developed to improve the precision and accuracy of CMB measurements. These advancements will help overcome current challenges and enhance our understanding of the universe. Despite these limitations, the CMB remains one of the most powerful tools in cosmology. Its data has revolutionized our understanding of the universe, and ongoing research continues to refine and expand this knowledge. The limitations highlight areas for future improvement and exploration in the quest to understand the cosmos. Controversies in the interpretation of cosmic microwave background data highlight the complexities of cosmology. One major controversy is the Hubble tension, where the Hubble constant measured from the CMB differs from that measured from local observations. This discrepancy challenges our understanding of cosmic expansion. The nature of dark energy is another area of debate. While the cosmological constant is a widely accepted explanation, alternative theories like quintessence propose a dynamic form of dark energy. Differentiating between these models remains a significant challenge. The interpretation of B-mode polarization is also contentious. Early claims of detecting primordial B-modes, indicative of inflation, have faced scrutiny and debate over potential contamination from galactic dust. This highlights the difficulty of extracting clear signals from complex data. Cosmic inflation itself is a topic of debate. While it explains many features of the CMB, some scientists argue that alternative models, such as cyclic or ekpyrotic universes, could also account for these observations. These alternatives challenge the dominance of inflationary theory. Foreground contamination from our galaxy poses another controversy. Different teams use various methods to remove this contamination, leading to slight differences in the interpreted CMB data. These variations can affect conclusions about fundamental cosmological parameters. The interpretation of small-scale anomalies in the CMB, such as the cold spot, is debated. Some propose these features could be due to large-scale structures or other astrophysical phenomena, while others suggest they might hint at new physics beyond the standard model. There is also ongoing debate about the nature of dark matter. While the CMB supports its existence, the exact properties and composition of dark matter remain unknown. Different theoretical models propose various candidates, from WMAPs to axions, each with different implications. The impact of neutrinos on the CMB is another source of controversy. While their presence and small mass are acknowledged, the exact number of neutrino species and their influence on the CMB power spectrum are debated. These uncertainties affect estimates of cosmological parameters. The role of cosmic strings and other topological defects in the early universe is also contentious. Some interpretations of CMB data suggest their presence, while others do not. Resolving this debate is crucial for understanding the universe's initial conditions. The isotropy of the universe, suggested by the uniform CMB, is sometimes questioned. Observations of large-scale anomalies and hemispherical power asymmetry challenge the assumption of perfect isotropy, leading to discussions about the true nature of the cosmos. The interpretation of reionization signatures in the CMB involves debate. Different models propose varying timelines and processes for the reionization era. These differences impact our understanding of the formation of the first stars and galaxies. The use of different statistical methods to analyze CMB data can lead to controversies. Variations in techniques and assumptions can produce slightly different results, affecting the interpretation of key cosmological parameters. This underscores the need for robust and consistent analysis methods. The potential influence of unknown systematic errors in CMB measurements is a persistent concern. Identifying and correcting for these errors is challenging but essential for accurate interpretation. Debates over the extent of these errors highlight the complexities of precision cosmology. The inclusion of new physics in cosmological models based on CMB data is often debated. While some anomalies suggest the need for new theories, others argue that existing models can account for these observations. This debate drives ongoing research and theoretical development. These controversies illustrate the dynamic and evolving nature of cosmology. As new data and methods emerge, interpretations of the CMB continue to be refined and debated. This process is vital for advancing our understanding of the universe and addressing its deepest mysteries. Technical challenges in observing the cosmic microwave background are numerous and complex. One major challenge is achieving the necessary sensitivity and resolution to detect faint CMB signals. This requires highly sophisticated instruments and careful calibration. Minimizing instrumental noise is crucial for accurate CMB measurements. Even the most advanced detectors produce some level of noise, which can obscure the faint CMB signal. Engineers must design systems that reduce this noise as much as possible. Another challenge is the need for extreme temperature stability. Instruments observing the CMB must be kept at very low temperatures to reduce thermal noise. This often involves complex cryogenic systems that must operate reliably in space. The Earth's atmosphere poses significant obstacles to CMB observation. Atmospheric water vapor absorbs microwave radiation, making ground-based observations difficult. Observatories must be located at high altitudes or use balloon or satellite platforms to avoid atmospheric interference. Foreground emissions from our galaxy and other sources can contaminate the CMB signal. These emissions must be carefully modeled and subtracted from the data to reveal the true CMB. This process requires detailed knowledge of the foreground sources and their characteristics. The cosmic microwave background is incredibly uniform, so detecting its tiny fluctuations requires precise measurement techniques. Small errors in the instrument or data processing can lead to significant inaccuracies. Ensuring the precision of measurements is a continuous technical challenge. Calibration of the instruments is critical. Any slight miscalibration can result in incorrect data. Calibration requires precise reference sources and methods to ensure the instruments are accurately measuring the CMB. Gravitational lensing of the CMB by massive structures can distort the observed signal. While this lensing provides useful information about the universe, it also complicates the analysis. Correcting for lensing effects requires sophisticated modeling and computational techniques. Space-based observatories face additional technical challenges. Instruments must be designed to withstand the harsh conditions of space, including extreme temperatures, radiation, and micrometeoroid impacts. These factors complicate the design and operation of CMB observatories. The vast amount of data collected by CMB missions requires extensive processing and storage. Analyzing this data involves complex algorithms and significant computational power. Ensuring the data is accurately processed and stored is a significant technical challenge. Radiation from the Sun and other celestial bodies can interfere with CMB observations. Shielding instruments from this radiation and carefully planning observation schedules are necessary to minimize its impact. This requires precise engineering and operational planning. The limited lifetime of space missions is another challenge. Instruments degrade over time, and missions must collect as much data as possible within their operational lifespan. This necessitates careful planning and efficient use of resources. Maintaining the alignment of the instruments is critical for accurate observations. Any slight misalignment can affect the data quality. Engineers must design systems that maintain precise alignment over long periods. Deploying and commissioning space-based observatories involves significant technical risks. Any failure in the deployment process can jeopardize the entire mission. Rigorous testing and contingency planning are essential to mitigate these risks. Advances in technology continue to improve CMB observation capabilities. Innovations in detector sensitivity, data processing, and mission design help overcome these technical challenges. As technology progresses, our ability to observe and understand the CMB will continue to enhance. Alternative explanations to the standard cosmological model propose different mechanisms for the observed properties of the universe. One such explanation is modified Newtonian dynamics, or MOND, which suggests modifications to Newton's laws of motion to account for the behavior of galaxies without invoking dark matter. Another alternative is the theory of modified gravity, which includes models like tensor vector scalar gravity, or TVES. These theories propose changes to general relativity to explain the observed phenomena attributed to dark matter and dark energy. The idea of a cyclic universe offers a different perspective. In this model, the universe undergoes endless cycles of expansion and contraction, avoiding the need for a singular beginning. This theory challenges the traditional Big Bang model. Some theories propose that dark energy could be explained by a dynamic field rather than a cosmological constant. Quintessence is one such theory, suggesting that dark energy evolves over time, potentially affecting the universe's expansion in different ways throughout its history. The concept of extra dimensions in string theory offers another alternative. These additional dimensions could have significant effects on gravity and the behavior of the universe. The influence of these dimensions might explain some observations without the need for dark matter or dark energy. Alternative explanations also explore the possibility of varying physical constants. Some theories suggest that constants like the speed of light or the gravitational constant may change over time. These variations could potentially explain the observed acceleration of the universe. The hypothesis of a multiverse is another intriguing idea. This theory posits the existence of multiple universes with different physical laws and constants. Our universe's properties could be a result of a selection effect from a vast ensemble of universes. Emergent gravity is a theory that proposes gravity is not a fundamental force, but an emergent phenomenon from more basic interactions. This idea, developed by physicists like Eric Verlinde, offers a different explanation for the effects attributed to dark matter. The possibility of primordial black holes contributing to dark matter is also considered. These black holes, formed in the early universe, could account for some of the gravitational effects observed. This idea provides an alternative to particle-based dark matter theories. Some models explore the idea of dark fluid, a single entity that combines the effects of dark matter and dark energy. This fluid would have properties that vary with time and space, potentially explaining the observations attributed to both dark components. The holographic principle derived from theories in quantum gravity suggests that the universe might be described by a lower dimensional theory. This concept could lead to new ways of understanding cosmic phenomena without relying on traditional dark matter or dark energy explanations. Alternative explanations often challenge the foundational assumptions of cosmology. For example, questioning the Copernican principle, which assumes that the universe is homogeneous and isotropic, could lead to new interpretations of observational data. Some researchers explore the impact of large-scale inhomogeneities on cosmic observations. These inhomogeneities could affect measurements of the universe's expansion and the CMB, offering different explanations for the observed acceleration. Theories involving exotic particles, beyond those in the standard model of particle physics, also provide alternative explanations. These particles could interact with ordinary matter and radiation in ways that mimic the effects of dark matter and dark energy. While these alternative explanations are intriguing, they require rigorous testing and validation. Observational evidence and experimental data are crucial for evaluating their viability. The pursuit of these alternatives enriches our understanding and drives the advancement of cosmological theories. Ongoing debates in cosmology reflect the dynamic nature of the field. One major debate centers around the Hubble constant discrepancy. Measurements from the cosmic microwave background differ from those using local distance indicators, leading to questions about our understanding of cosmic expansion. The nature of dark matter remains a hotly debated topic. While the existence of dark matter is widely accepted, its exact composition is unknown. Scientists are exploring various candidates, from WIMPs to axions, but none have been definitively detected yet. Dark energy is another area of intense debate. The cosmological constant proposed by Einstein is the simplest explanation, but some scientists argue for a dynamic form of dark energy. Understanding its true nature is crucial for explaining the universe's accelerated expansion. The concept of cosmic inflation also sparks debate. Inflation theory explains the uniformity of the CMB and the large-scale structure of the universe, but some alternative models, such as cyclic universes, challenge this view. These alternatives propose different mechanisms for the early universe's expansion. The isotropy of the universe is questioned by observations of large-scale anomalies in the CMB. Features like the cold spot suggest possible deviations from perfect isotropy, leading to discussions about the universe's overall structure and symmetry. The role of neutrinos in cosmology is another ongoing debate. Their small but non-zero mass affects the formation of structures in the universe. Understanding their exact properties and number is essential for refining cosmological models. The search for primordial gravitational waves continues to be a topic of interest. Detecting these waves would provide strong evidence for inflationary theories. However, separating these signals from other sources of noise remains a significant challenge. Modified gravity theories offer alternatives to dark matter and dark energy. These theories propose changes to general relativity to explain cosmic phenomena. The debate over their validity continues as more observational data is collected. The nature of the reionization era is also debated. Different models propose varying timelines and mechanisms for the reionization of the universe. Understanding this era is crucial for learning about the formation of the first stars and galaxies. The interpretation of B-mode polarization in the CMB is another area of discussion. While it can provide evidence for primordial gravitational waves, separating it from foreground contamination is difficult. This ongoing challenge fuels debates about the interpretation of CMB data. The possibility of a multiverse adds a philosophical dimension to cosmological debates. If multiple universes exist with different physical laws, it could explain the fine-tuning of our universe. However, testing this hypothesis remains a significant challenge. The impact of large-scale inhomogeneities on cosmic observations is still being explored. These inhomogeneities could affect measurements of the universe's expansion and the CMB. Understanding their influence is crucial for accurate cosmological models. The role of exotic particles beyond the standard model is also debated. Discovering these particles could provide new insights into dark matter and other cosmic phenomena. Experimental efforts are ongoing to detect such particles. Debates about the nature of the Big Bang itself persist. Some theories suggest alternatives to the singularity, such as a pre-existing state or a bounce from a previous universe. These ideas challenge the conventional understanding of the universe's origin. Ongoing debates in cosmology drive the field forward. As new data is collected and theories are tested, our understanding of the universe continues to evolve. These discussions are essential for advancing scientific knowledge and uncovering the mysteries of the cosmos. In this video, we delved into the fascinating world of the cosmic microwave background, CMB, and its critical role in our understanding of the universe. We began by defining the CMB, tracing its discovery, and highlighting its importance in cosmology. The early efforts of key scientists set the stage for our current understanding and ongoing research into this ancient cosmic relic. We explored the Big Bang theory, discussing how the CMB serves as crucial evidence supporting this model of the universe's origin. We also examined alternative theories and placed these ideas in a historical context, emphasizing how our understanding has evolved over time. Next, we delved into the characteristics of the CMB, including its temperature, uniformity, and the significant anisotropies that provide a wealth of information about the early universe. The spectrum of the CMB and the sophisticated techniques used to measure it were also covered, showcasing the precision and complexity of modern cosmological observations. We highlighted the pivotal discoveries made by Penzias and Wilson, whose work set the stage for later missions such as COBE, WMAP, and Planck. These missions have provided detailed maps of the CMB, revealing its intricate structure and offering insights into the early universe. The physics behind the CMB, including photon decoupling, the recombination era, blackbody radiation, and the Sachs-Wolfe effect, were explained to illustrate the fundamental processes that shape the CMB. We also discussed the significance of CMB anisotropies and their implications for the large-scale structure of the universe. We examined the methods used to map the CMB and the data analysis techniques that allow scientists to interpret these maps accurately. The findings from these maps have been pivotal in determining the age of the universe and understanding its composition, including the roles of matter, and dark energy. We covered the challenges and controversies in interpreting CMB data, addressing the technical difficulties in observation and the ongoing debates in cosmology. These discussions underscore the dynamic and evolving nature of the field, highlighting the importance of continuous research and technological advancement. Looking to the future, we explored upcoming satellite missions and advances in observation technology. These missions promise to bring new discoveries, enhancing our understanding of the universe's earliest moments and the fundamental forces shaping its evolution. International collaborations were also emphasized, showcasing how global cooperation is crucial for advancing our knowledge. These partnerships enable the sharing of resources and expertise, driving forward the scientific pursuit of understanding the cosmos. Finally, we discussed the potential breakthroughs that could emerge from ongoing and future research, from understanding dark matter and dark energy to discovering extraterrestrial life and unifying fundamental theories, the future of cosmology is filled with exciting possibilities. If you enjoyed this deep dive into the cosmic microwave background and the mysteries of the universe, please like and subscribe to our channel. Don't forget to check out the rest of our videos for more fascinating insights into the world of astronomy and cosmology. Thank you for watching, and we look forward to exploring the universe with you in our future videos.